Hello there and welcome to Science for Sleep, where curiosity gets comfortable, science slows down, and even the strangest corners of the universe are allowed to take their time. Tonight, we are drifting toward a black hole that does something. Black holes are not usually polite enough to do. It erupts, rests, and erupts again. Not at random, not just once, but in a repeating pattern that has made astronomers lean closer to their screens and say, in the careful language of science, well, that is odd. The name for this behaviour is a quasi-periodic eruption, or QPE, which sounds a little like a technical fault in a washing machine, but is actually one of the most curious signals we have found coming from the centres of distant galaxies. These eruptions appear as bright bursts of X-rays, the kind of high-energy light we cannot see with our eyes, but can detect with space telescopes floating above Earth's atmosphere. A black hole sits at the heart of a galaxy, quiet for a while, and then suddenly the X-rays rise. The glow strengthens, the system flares, then it fades again. Hours later, or days later, it happens once more. The pattern is not perfect enough to be called a strict clock, but it is regular enough to make the word clockwork feel tempting. It is as if something near the black hole is keeping a schedule, though perhaps the schedule was written by someone who occasionally forgets where they put their glasses. And that is the lovely little mystery waiting for us tonight. We are not looking at a black hole simply eating matter in one dramatic feast. We are looking at something that may be fed in pulses. Something may be orbiting. Something may be dipping through a hot disk of gas. Something may be brushing close to the edge of gravity again and again, each visit producing a flare bright enough to cross millions or even billions of years of space, before finally landing in our detectors as a tiny message from the dark. Before we move closer to it, I would love to know where you are listening from tonight. Are you somewhere quiet with the lights low? Are you in bed, on a sofa, in a warm room, or maybe half listening while the rest of the house settles down? And because this story is about eruptions that keep returning on a schedule, what time is it where you are right now? Not cosmic time, not telescope time, just your little corner of the evening with your own clock glowing softly nearby, doing its best to keep up with the universe. If you find this kind of slow science soothing, or if you enjoy letting big cosmic questions become calm enough to fall asleep beside, I would be very grateful if you gave the video a like, subscribed, or left a quiet comment. It helps this small, sleepy observatory reach other people who might enjoy a peaceful journey through space without being asked to solve equations in their pajamas. And do not worry, we will not rush. Black holes may be dramatic, but we are under no obligation to match their energy. So settle in, loosen your thoughts, and let the idea arrive slowly. Somewhere far away, in the crowded centre of a galaxy, a massive black hole is surrounded by gas so hot that it shines in X-rays. This gas does not fall inward neatly, like water down a drain. Near a black hole, matter is pulled, stretched, heated, stirred, and forced into a bright spinning disk. That disk can behave in ways that are still difficult to predict, and hidden in that disk, or perhaps moving through it, may be the key to a cosmic pulse that keeps coming back. A black hole itself, of course, does not shine. That is one of the first strange things to remember. The dark centre is dark because beyond the event horizon, light cannot climb back out. But the region around the black hole can be one of the brightest places in the universe. Gas falling inward does not simply drop like a stone. It swirls. It rubs against other gas, it heats up through friction and compression, until it becomes a brilliant, restless structure called an accretion disk. You can imagine it, loosely, as a record spinning around a hole in the middle. Though this record is made of plasma, is hotter than any oven, and is not something you should try to put on a turntable. Most of the time, when people picture a black hole feeding, they imagine a steady process. Matter gets too close, forms a disk, heats up, and gradually spirals inward. But the universe often has more interesting habits than our first mental picture allows. Sometimes the feeding is messy. Sometimes the disk may become unstable. Sometimes a star gets too close and is torn apart in what astronomers call a tidal disruption event, and sometimes, after that kind of destruction, the leftover gas may keep circling the black hole like a bright uneven ring of debris. In a few rare cases, instead of one single flare that fades away, astronomers see repeated flashes. The light rises, falls, waits, and rises again. That repeating behaviour is what makes QPS so fascinating. The Q matters. Quasi means almost. A QPE is not a perfectly regular tick-tock like the second hand on a clock. It is more like someone tapping a table in a rhythm that keeps returning, but not with machine-perfect timing. The delays can shift. The eruptions can grow stronger or weaker. Their shapes can change. Yet the pattern is still clear enough to suggest that something physical is repeating. In astronomy, repetition is precious. A single flash can be mysterious, but a repeating flash is a clue you get to watch more than once. It gives scientists another chance, and another, and perhaps, if the telescope schedule behaves itself, another after that. One of the early famous examples came from a galaxy known as GSN 069. At its centre sits a supermassive black hole, though by supermassive black hole standards it is on the lighter side. That is a slightly ridiculous sentence, like calling an elephant a small household object, but astronomers have to compare monsters with other monsters. In this system, bursts of X-rays were seen returning roughly every 9 hours. The black hole seemed to brighten again and again, almost as if it were taking regular meals. NASA even described it with the memorable idea of a black hole having 3 hot meals a day, which is probably the closest a supermassive black hole has ever come to being accused of following a meal plan. During those eruptions, the X-ray brightness increased strongly, and the gas near the black hole appeared to grow hotter. Then the system faded back toward a quieter state. The obvious question is simple, which is often how the best questions begin. Why would that happen? Why would a black hole brighten, calm down, and then brighten again? If matter is falling in, why not flare once, or glow steadily, or behave in some other familiar way? What is setting the rhythm? Scientists have several ideas, and part of the fun is that none of them has completely won yet. One possibility is that the accretion disk itself has a kind of cycle. Matter may build up in the disk until conditions tip, and then a burst of material moves inward, releasing energy as X-rays. After that, the disk resets, matter builds again, and the process repeats. This would make the black hole's surroundings a little like a kettle that keeps reaching a boil, calming down and heating again, though with much more gravity and considerably less chance of making a pleasant cup of tea. Another possibility is more dramatic. There may be an object orbiting the black hole, perhaps a star, a stellar remnant, or even a smaller black hole, moving through the accretion disk on a tilted path. Each time it plunges through the disk, it disturbs the gas and creates a splash of hot material. If the orbit carries it through the disk again and again, then each crossing could produce another flare. This picture is surprisingly easy to imagine. Think of someone diving into a pool, climbing out, circling around and diving back in. Every entry makes a splash. Near a black hole, the pool is a disk of glowing gas, the diver may be a star, and the splash is not water, but a burst of X-rays. It is not a relaxing swimming lesson, but it is a very useful image. This model became especially interesting when astronomers connected some QPEs with tidal disruption events. In a tidal disruption event, a star wanders too close to a supermassive black hole and gets stretched by gravity until it is torn apart. Some of the star's material escapes, some of it falls into orbit, forming a disk or stream of debris. If another object remains nearby, or if part of the disrupted star survives in some form, repeated interactions with that debris could create recurring eruptions. The idea is still being tested, but it gives scientists a way to link two strange black hole behaviours that once seemed separate. Then there is the more recent case of a galaxy called SDS S 1335 plus 0728, nicknamed Ansky. which had been fairly quiet for years before it began to brighten and show extreme QPE-like eruptions. This is especially interesting because it suggests that QPEs may not only happen after a star is visibly torn apart. They may also appear when a black hole is waking up, when a new accretion flow is forming, or when gas around the black hole changes into a state that can produce repeated flares. Ansky's eruptions have been longer and more energetic than typical QPEs, which is both exciting and inconvenient, because astronomers generally prefer mysteries that do not immediately make their models feel underdressed. That is where we are with QPEs right now. We know they are real, we know they come from galactic centres, we know they appear in X-rays, we know they repeat, we know they involve supermassive black holes and hot gas close to extreme gravity. But we do not yet know the full mechanism. That is not a weakness of the story. That is the story. Science is often most alive in the space between a clear observation and a complete explanation. A telescope sees a pattern. A team checks it. Another telescope confirms it. Theories arrive, each carrying a little lantern. Some lamps burn brighter than others. And slowly, carefully, the dark room becomes easier to describe. For sleep, there is something almost comforting about that. Not because black holes are gentle, they are not. They are regions where gravity has become so strong that our usual ideas about space and time are pushed to their limits. But the way we study them is careful and patient. A flare appears. We measure its brightness. We check how long it lasts. We wait for the next one. We compare the time between eruptions. We watch whether the bursts drift, weaken, strengthen, or change colour in X-ray light. It is not unlike listening to a strange sound in a quiet house and realising it happens every few minutes. At first it is unsettling. Then you begin to count. Then you begin to learn the pattern. And once there is a pattern, the mystery becomes something you can approach. The phrase, black hole that erupts like clockwork, is useful, but we should hold it gently. QPEs are not clockwork in the neat mechanical sense. They are not gears turning in a polished brass case. They are more like natural rhythms produced by orbits, disks, heat and gravity. The timing may come from the path of an object circling the black hole. It may come from a disk repeatedly becoming unstable. It may come from a combination of both. The word clockwork helps us picture regularity, but the word quasi reminds us not to make the universe tidier than it really is, and perhaps that is why QPEs are so appealing. They sit between order and chaos. A black hole is one of the most extreme objects we know, and yet here it may be producing a repeatable signal. Not a random roar, but a pulse. Not a steady lamp, but a flare that returns. Somewhere near the event horizon, matter is moving through a pattern written by gravity. The pattern is not perfectly simple, but it is not meaningless either. It is the kind of clue that makes astronomers patient. It says, keep watching. X-ray telescopes are especially important here because these eruptions are mostly invisible to ordinary optical telescopes. If you looked at the host galaxy in visible light, you might not see anything obvious changing at all. The action is happening in high-energy radiation, produced by extremely hot material close to the black hole. Earth's atmosphere protects us from most X-rays from space, which is excellent for life and inconvenient for astronomy. So we place telescopes above the atmosphere, in orbit, where they can catch the light before our protective sky absorbs it. Instruments like XMM Newton, Chandra, NICER, Swift and others have helped astronomers watch these strange bursts and build a timeline of their behaviour. That timeline matters because QPEs are not just pretty flashes, they may become tools. If a small object is orbiting a supermassive black hole and repeatedly interacting with a disk, then the timing of the eruptions could reveal details about the orbit. The flare shape could tell us about the disk. The temperature could reveal how much energy is released. Changes over months or years could show whether the orbit is shrinking, whether the disk is evolving, or whether the system is slowly running out of material. In the future, some of these systems may even be connected with gravitational waves, tiny ripples in space-time created by massive objects moving around one another. That means QPEs might help us link light-based astronomy with gravitational wave astronomy, giving us two very different ways to listen to the same deep cosmic machinery. At first, the signal did not announce itself like a grand cosmic event. It was not a galaxy exploding across the sky. It was not a bright new star visible to backyard telescopes. It was a small change in X-ray light from the center of a distant galaxy, the sort of thing that only a space telescope would notice, and only because it was built to notice exactly that kind of quiet, high-energy mischief. Somewhere far beyond the soft blue edge of Earth's atmosphere, a detector saw the X-ray brightness rise. Then it fell. That alone was interesting, but not shocking. Black holes and the gas around them can flicker, they can brighten, they can fade, they can behave like a faulty lamp in a very expensive cosmic hallway. Then the light came back. That was the part that made astronomers pause. A single flare can be explained in many ways. A black hole might swallow a clump of gas. A star might pass too close. A disk of hot material might shift, heat, or cool. Space is full of one-time events, and astronomers are used to catching a glimpse of something dramatic after the main action has already happened. But when a flare returns, when it appears, fades, waits, and then appears again, the question changes. It is no longer only, what caused this? It becomes, what is causing this again? That one little word, again, is powerful. Again means there may be a rhythm. Again means there may be a cycle. Again means the universe has handed you not just a flash, but a pattern. And patterns are what scientists love most, even if they pretend to be calm about it in papers with very serious titles. A repeated signal gives you something to compare. You can measure the space between the bursts. You can ask whether the second one looks like the first. You can check whether the third one arrives early, late, stronger, weaker, hotter, cooler, shorter, or longer. A repeated flare is like hearing a strange knock in the night, and then hearing it again at nearly the same interval. You may still not know who is at the door, but now you know they are not simply walking past. The first known quasi-periodic eruptions were found in X-ray observations of galactic centers, where supermassive black holes sit surrounded by stars, gas, dust, and all the busy clutter of a galaxy's middle. These black holes are not the small stellar mass black holes formed from collapsed massive stars. They are far larger, with masses measured in hundreds of thousands, millions, or even billions of suns. And yet even a supermassive black hole can be surprisingly hard to notice if it is not actively feeding. A quiet black hole in a distant galaxy is not like a glowing sign. It is more like a dark drain in a crowded city at night. You infer it from the motion around it, from sudden activity, from the way matter behaves when it gets too close. The eruption itself is not coming from inside the black hole. That is important, and worth holding clearly. Nothing we see comes out from beyond the event horizon. Once light crosses that boundary, it does not return. The flash comes from outside, from matter near the black hole, where gravity is strong enough to whip gas into fast motion and heat it to temperatures that glow in X-rays. X-rays are not visible to human eyes, and Earth's atmosphere blocks most of them before they reach the ground, which is very considerate of the atmosphere from a survival point of view. Unfortunately, it also means we need telescopes in space to study them. So when astronomers talk about seeing a QPE, they do not mean someone looked up and saw a black hole blinking. They mean instruments above the atmosphere measured high-energy light rising and falling from a galaxy's center. That may sound technical, but the basic picture is wonderfully simple. Imagine watching a distant lighthouse through fog. Most of the time you see little or nothing. Then, for a short time, a beam swings into view. It fades, you wait. After a while, the beam returns. If it happens once, perhaps it was a trick of the weather. If it happens again and again, you begin to suspect something is turning. With QPEs, something near the black hole seems to be turning, building, striking, crossing, heating, or releasing energy in a repeating way. The exact cause remains uncertain, and that uncertainty is part of what makes the subject so alive. In science, a mystery is not simply a blank space. A good mystery has boundaries, it has clues, it has observations that rule out some ideas and keep others standing. QPEs are like that. They are not random flashes from anywhere in space. They are found at the centres of galaxies. They appear in soft X-rays. They rise and fall on timescales humans can actually watch, from minutes to hours or days, rather than millions of years, which is a refreshing change in astronomy. And they repeat. The first time you hear that, it may not sound especially strange. Many things in the universe repeat. Planets orbit stars. Moons orbit planets. Pulsars spin and flash with extraordinary precision. Binary stars eclipse each other. Comets return, sometimes after long absences, like relatives who send no messages and then appear at dinner. So why should a repeating black hole flare be surprising? Because black holes are messy eaters. The gas near them is not moving through a neat mechanical clock. It is hot, turbulent, magnetic, stretched, compressed, and often unstable. Matter in an accretion disk does not behave like beads on a wire. It behaves more like boiling soup on a spinning plate, except the soup is plasma, the plate is gravity, and the kitchen is several million degrees too enthusiastic. That is why a clean repeated X-ray eruption stands out. It suggests that something is organising the chaos. The repetition might come from an orbiting object. It might come from a cycle in the accretion disk. It might come from a star that lost material and left behind a surviving core that continues to interact with gas. It might involve a smaller compact object moving around a much larger black hole. The details differ from model to model, but nearly all of them share one idea. Something near the black hole is not happening just once. It is returning to a similar condition again and again. In one famous system, GSN 069, astronomers saw X-ray eruptions repeating on a rough schedule of hours. The black hole would sit in a dimmer state, then brighten sharply in X-rays, then fade again. After a pause, the pattern returned. The timing was regular enough to be startling, but not perfect enough to be simple. That is why the word quasi matters. Quasi-periodic does not mean perfectly periodic, it means almost periodic. The eruptions have a rhythm, but the rhythm can shift. One interval may be a little shorter, another may be a little longer. One flare may rise more quickly, another may decay more slowly. If a pulsar is a metronome, a QPE is more like a sleepy drummer who knows the beat but occasionally gets distracted by gravity. Still, even an imperfect rhythm is useful. Astronomers can make what is called a light curve, which is simply a graph of brightness over time. The name sounds elegant, but the idea is practical. Brightness on one side, time on the other. When the flare begins, the line rises. When it fades, the line falls. If the flare returns, the line rises again. In a QPE light curve, you see a sequence of these rises and falls, like small hills across a plain. From those hills, scientists can measure how long each eruption lasts, how bright it gets, how quickly it climbs, how slowly it drops, and how much time passes before the next one arrives. There is something calming about a light curve, even when it represents a violent process. It takes a black hole eruption and turns it into a line you can follow with your eyes. The actual event may involve gas moving at enormous speeds near a region of extreme gravity, but the data arrives as a patient trace. A rise, a peak, a fall, a quiet interval, another rise. In that simple shape, a distant black hole becomes almost readable, not fully understood perhaps, but readable enough to invite questions, and the questions came quickly. If the eruptions were caused by disk instabilities, what kind of instability could repeat so sharply? If an orbiting object was involved, what was it? A normal star? A white dwarf? A neutron star? A stellar mass black hole? How close did it pass to the supermassive black hole? Was it losing material each time? Was it punching through a disk, stirring gas into shocks? Was the accretion disk newly formed, perhaps after the destruction of a star, or had it been there already, thin and faint, waiting for something to disturb it? The difficulty is that we cannot fly there and look. We cannot send a probe into a galactic nucleus and ask it politely to take a closer photograph of the object responsible. Even if we could build such a probe, the journey would take far longer than anyone's bedtime routine should be expected to cover. So astronomers work with light. They gather X-rays, optical light, ultraviolet light, infrared light, and sometimes radio waves. They compare what brightens and what does not. They check whether the host galaxy shows signs of an active galactic nucleus, or whether it looks mostly quiet. They search old telescope archives to see if anything happened before. In astronomy, archives are a little like the cupboards where the universe leaves receipts. This matters because some QPE sources appear in galaxies that do not show the usual signs of a black hole that has been steadily feeding for a long time. That is surprising. If a black hole has a large active accretion disk, then repeated X-ray behavior might feel easier to place within that ongoing activity. But if the galaxy looked quiet, and then these bursts appeared, scientists have to explain how the necessary hot gas got there, and why it is behaving in such a specific way. Perhaps a star was disrupted. Perhaps a disk formed recently. Perhaps there was always a small flow of matter, too faint to stand out until something began disturbing it. The phrase "strange little flash" may sound gentle, but the energy involved is not small in human terms. These are X-ray bursts from the neighbourhoods of supermassive black holes. They can release enormous amounts of energy. They are only little from our point of view because they are very far away, and because the universe contains explosions and outbursts so huge that even a black hole flare can become little by comparison. Astronomy has a habit of making the word small work very hard. A small black hole may still outweigh the sun many times over. A short eruption may still release more energy than anything on Earth could dream of producing. A nearby galaxy may still be millions of light years away. It is a field where adjectives need supervision. What makes the QPE flash feel small is not its energy, but its subtlety. It does not dominate the night sky. It does not announce itself to human senses. It is found through careful watching. A telescope records an X-ray source. A researcher notices unusual variability. Another observation confirms it. A pattern emerges from numbers. The discovery is not a single dramatic moment with thunder in the background. It is closer to someone looking at a graph and realizing the graph is trying to tell them something. That is often how modern astronomy works. The universe does not always reveal itself in grand images. Sometimes it appears in a table, a curve, a repeated measurement, a faint source that brightens when no one expected it to. It can be easy to forget that behind every beautiful space image there is a great deal of counting. Photons arrive one by one. Instruments record them. Software sorts them. Scientists remove background noise, check calibration, compare timestamps, and ask whether the signal is real. The wonder is still there, but it wears practical shoes. For QPEs, timestamps are especially important. If you want to know whether something repeats, you need to know when each flare began and ended. You need to know whether the intervals form a pattern. You need to be careful, because telescopes cannot stare at every source all the time. Space observatories have schedules. Earth can block the view. Instruments have limits. Background radiation can interfere. Sometimes the telescope catches only part of an eruption, like walking into a room just as someone finishes telling the funniest part of a story. Scientists then have to reconstruct what likely happened before and after, using the data they have rather than the data they wish they had. This is one reason QPEs are both exciting and inconvenient. They happen on timescales short enough to study, but not always neatly enough to catch. If eruptions repeat every few hours, you need long observations. If they repeat every few days, you need patience and coordination. If the timing drifts, you need flexibility. The telescope has to be looking at the right galaxy at the right time, in the right energy band, for long enough to see the rise and fall. It is not quite cosmic birdwatching, but there is a similar mood to it. You know the rare bird may return to the branch. You know roughly when. You set up your instrument. You wait. You try not to sneeze. The return of the flash is what turns waiting into discovery. One burst says, something happened. Two bursts say, something may be happening in a cycle. Three bursts begin to feel like a system. More bursts let you test ideas. Does the brightness change from flare to flare? Does the temperature increase at the peak? Does the waiting time depend on how strong the previous eruption was? Does the shape look symmetrical, rising and falling evenly, or does it rise fast and decay slowly? These details matter because different physical causes leave different fingerprints. If an object is passing through an accretion disk, the eruption might be linked to impact. Each crossing could heat gas and launch material out of the disk. The flare timing would then be tied to the object's orbit, though the orbit itself might shift because strong gravity near a black hole does not behave like the simple ellipses drawn in schoolbooks. Orbits close to a supermassive black hole can precess, meaning the path turns over time instead of repeating exactly. That could help explain why QPEs are regular, but not perfectly regular. The object returns, but not along a perfectly closed track. The clock keeps time, but the gears are made of warped space-time. If, on the other hand, the disk itself is cycling, then the eruption might be more like a repeated release of built-up energy. Gas accumulates. Conditions change. A hot inner flow brightens. The disk cools or drains. Then the process begins again. This kind of model does not require a separate object plunging through the disk, but it must explain the observed timing, strength and shape of the bursts. Some QPE observations have challenged simple disk instability explanations, especially when the eruptions are strongly asymmetric or when they occur in galaxies without obvious long-term active black hole behavior. That does not mean disk physics is irrelevant. Near black holes, disk physics is almost always relevant. It means the disk may not be acting alone. A third possibility connects QPEs to the aftermath of a tidal disruption event. In that situation, a star passes too close to a supermassive black hole and is pulled apart by tidal forces. Some material falls back toward the black hole, forming a stream or disk. The initial flare may fade over months or years, but the debris environment can remain. If another object or surviving core moves through that material, repeated eruptions could appear later. This idea is attractive because it gives the black hole both a supply of gas and a reason for changing behavior over time. It also explains why astronomers search older observations. A QPE seen today may have a backstory written years earlier in optical or ultraviolet light. Notice how the mystery becomes less like a single locked box and more like a room with several doors. Behind one door is an orbiting object striking a disk. Behind another is a disk instability. Behind another is a star that was partly or fully torn apart. The correct explanation may not even be the same for every QPE source. Nature is under no contract to use one mechanism just because it is convenient for our PowerPoint slides. Some systems may involve one cause. Others may involve a combination. A newly awakened black hole may not behave like a long-active one. A smaller supermassive black hole may produce different timescales than a larger one. The disk may be thick or thin, fresh or old, tilted or warped. The orbiting object, if there is one, may be a star, a compact remnant, or something else still hiding in the math. For a listener settling down to sleep, this may sound like a lot of uncertainty. But uncertainty in science is not the same as confusion. It is more like careful mapping. We know where the coastline is. We know there are mountains inland. We know some roads are blocked. We are still drawing the details. QPEs are young as a field of study. Only a small number have been found compared with many other astronomical classes, Every new source matters. Every new flare matters. A single well-observed eruption can sharpen a model. A full sequence of eruptions can change the discussion entirely. That is why the strange little flash that came back again matters so much. It gave astronomers a new kind of black hole behaviour to study. Not just feeding, not just flaring, repeating. It suggested that close to a supermassive black hole, where gravity is strong and matter is hot, there may be systems acting like natural laboratories. They may let us study how accretion disks respond to repeated disturbance. They may reveal hidden orbiting objects too small or too dark to see directly. They may point toward extreme mass ratio in spirals, where a small dense object slowly spirals around a massive black hole. And because those systems are also expected to produce gravitational waves, QPEs may one day help connect X-ray astronomy with a completely different way of sensing the universe. Once astronomers had seen the light return, the next instinct was to count. Not in a dramatic way, not with someone standing beside a telescope whispering numbers under their breath, though that would be quite charming. The counting happened in data, in the careful timing of X-ray photons arriving from a galaxy so far away that the eruption had already finished long before the light reached us. A flare appeared. It faded. The telescope kept watching. Another flare appeared, then another. Slowly, the strange little flash stopped looking like a one-time surprise and started looking like a signal with a schedule. That is when the idea of a black hole behaving like a cosmic alarm clock begins to make sense, though of course we should be gentle with the comparison. A bedside alarm clock is designed to help you wake up at a certain time, or at least to give you something to be irritated with before breakfast. A black hole is not designed for anything, and if it wakes something up, the result is usually not a refreshing start to the day. But the image is useful because QPEs repeat. They rise in brightness, fade away, wait for a while, and then rise again. The timing is not perfect, but it is persistent. It is as if some process near the black hole keeps returning to the same point in a cycle, and every time it does, it rings in X-rays. This is the part that makes QPEs feel different from many other black hole events. A tidal disruption event, for example, is usually thought of as a dramatic one-time disaster. A star gets too close to a supermassive black hole, tidal forces stretch it, and some of its gas forms a glowing stream or disk. The black hole brightens, and then, over time, fades. There can be complexity in that fading. There can be bumps and changes and long afterglows. But the basic story is one event. A QPE adds repetition. It asks us to imagine not only a violent environment, but a repeating mechanism inside that environment. Something is not merely falling once. Something is orbiting, rebuilding, crossing, cooling, heating, or being disturbed again and again. In astronomy, timing is often the clue that gives the game away. If a star dims at regular intervals, perhaps a planet is passing in front of it. If a radio signal pulses many times per second, perhaps a neutron star is spinning. If two stars eclipse each other, their brightness changes according to their orbit. If a black hole's X-ray light erupts again after a roughly similar pause, then timing becomes the first doorway into the physics. The light curve becomes less like a photograph and more like a clock face, though the hands are made of hot gas and the numbers have been replaced by gravity. The word periodic sounds neat. It suggests something that repeats at fixed intervals, like a pendulum swinging or a clock ticking. The word quasi-periodic is a little more honest. It means the signal repeats, but not with perfect precision. The waiting times may shift. The flare shapes may vary. One eruption may be brighter than the one before it. Another may rise more slowly or fade more quickly. That slight imperfection matters. It tells us the system is not a simple machine. It is not a clean gear turning in isolation. It is a natural process happening in a turbulent environment, with gas, heat, magnetic fields, orbital motion, and strong gravity all involved at once. If the universe has built an alarm clock here, it has built it inside a storm. Think for a moment about what it means for anything to keep time near a black hole. Around Earth, we are used to clocks behaving politely. The clock on the wall, the one in your phone, the one on the microwave that may or may not still be blinking because no one reset it after a power cut, all of them share a familiar world. Gravity is weak. Speeds are slow compared with light. Space and time feel stable enough that we can make appointments, miss them, and blame traffic. Near a supermassive black hole, the situation is less forgiving. Gas can orbit at a significant fraction of the speed of light. Space-time is curved. Orbits can twist instead of closing neatly. Matter heats to millions of degrees. The closer you get to the event horizon, the more the ordinary habits of time and motion begin to feel like local customs rather than universal laws. And yet, in that extreme region, repetition appears. That is remarkable. It means some physical scale is imprinting itself on the light. It may be the orbital time of an object moving around the black hole. It may be the time it takes gas in the disk to heat, cool, or move inward. It may be a beat created when two motions overlap, like the way two slightly different rhythms can create a pattern that comes and goes. The timing becomes a measuring tool. If eruptions return every few hours, that tells us the responsible process is happening close to the black hole, because things farther out usually orbit more slowly. In a galaxy, stars can take thousands or millions of years to circle the centre. Near the black hole, the clock speeds up. Hours begin to mean extreme closeness. This is one reason QPEs are so valuable. They operate on humanly watchable timescales. So much of astronomy asks us to think in centuries, millions of years, or billions of years. Galaxies merge slowly. Stars evolve over lifetimes far beyond ours. The universe expands with a patience that makes even the most relaxed person look impatient. But QPEs can change during a single telescope observation. A flare may rise and fade in about an hour. Another may appear later the same day. That gives astronomers the rare chance to watch a black hole system doing something in real time, or at least as real as time can be when the light has travelled across intergalactic distances. When GSN 069 became famous for its repeating eruptions, part of the excitement came from the rhythm. The X-ray burst returned roughly every 9 hours, and each eruption lasted on the order of an hour. That is short enough for a researcher to follow during a workday, though perhaps not the most restful workday. The brightness could increase dramatically compared with the quieter level between eruptions. Then it would settle back down. If you plotted the X-ray count rate, the eruptions would stand like repeated hills, separated by valleys. The hills were not identical, but they belonged together. They looked like the same system performing the same act more than once. To understand why this feels like an alarm clock, imagine listening to a house at night. Most of the time, there is silence. Then the heating system clicks on. It hums for a while. It clicks off. Later, it happens again. You may not understand the whole plumbing arrangement, but you recognize a cycle. Something triggers, something runs, something stops, something resets. QPEs invite the same kind of thinking, though the house is a galactic nucleus, and the heating system is matter being energized near a supermassive black hole. The comparison is not perfect, but it gives us a foothold. The universe is making a repeating noise in X-rays, and we're trying to understand what machinery could produce it. One possible clock is an orbit. Orbits are natural timekeepers. The Moon orbits Earth. Earth orbits the Sun. The stars near the centre of our own galaxy orbit the Milky Way's central black hole. If an object is circling a supermassive black hole on a path that crosses or grazes an accretion disk, then each passage could produce a flare. This is one of the most appealing ideas because it connects the repeated eruption to a repeated position. The object returns to the disk. The gas is disturbed. A burst of X-rays follows. The object continues its orbit. The system quiets. Later, the object comes back. The object itself could be several things depending on the model. It might be a star, though a normal star passing very close to a black hole faces serious dangers. It can be stripped of gas, it can be stretched, it can lose mass each time it approaches. It might be a white dwarf, the dense leftover core of a star like the Sun. It might be a neutron star, an even denser remnant. It might be a stellar mass black hole, small compared with the central monster, but still massive enough to disturb gas strongly as it moves. Each option has its strengths and problems. A normal star is easier to form in some environments, but harder to keep intact if the orbit is too extreme. A compact object can survive harsher conditions, but may be harder to detect except through its effects. The data acts like a set of footprints, and scientists are still working out what kind of creature made them. If the orbiting object model is right, the black hole is not really the alarm clock by itself. The whole system is. The central black hole provides the gravity. The accretion disk provides the glowing gas. The smaller object provides the repeating disturbance. The X-ray telescope hears the ring. Take away any one of those pieces and the pattern may vanish. This is important because black holes are often described as if they act alone, but many of the most interesting black hole signals come from relationships. A black hole and a star, a black hole and a disk, two black holes in orbit, a compact object moving through gas. Gravity makes partnerships, though not always gentle ones. Another possible clock is inside the disk. Accretion disks are not smooth, passive structures. They can become unstable. Gas can pile up in one region, heat, change opacity, move inward, or trigger a transition in the flow. In some systems, disks produce outbursts because matter accumulates until a threshold is reached, then drains inward and releases energy. This happens in other kinds of accreting objects too, such as certain binary star systems, though the details near a supermassive black hole are very different. If QPEs come from disk cycles, the alarm is not an orbiting object striking the disk. It is the disk itself repeatedly changing state. That idea has a certain tidiness. Matter builds up. A burst happens, matter is depleted or rearranged. The system resets. But the challenge is explaining the details. QPEs can have large amplitudes, relatively short durations, and distinctive temperature changes. Their timing can be regular enough to suggest a stable driver, yet flexible enough to resist a simple clock. Some sources also appear in galaxies that were not obviously active before, which raises the question of where the disk came from and why it would suddenly begin cycling in such a dramatic way. A disk instability may still be part of the answer, but many scientists suspect that something else may be helping set the rhythm. A third clock may begin with a star that came too close and left debris behind. If a tidal disruption event created a disk or stream of gas around the black hole, that debris could become the material that later erupts. The timing might be connected to a surviving stellar core, a compact object, or another star moving through the debris. In this picture, the first disaster prepares the stage, and the later QPEs are repeated disturbances in the leftover material. This would make the alarm clock not a permanent fixture but a temporary arrangement. It rings for a while, perhaps months or years, and then fades as the debris thins out. The orbit shifts, or the interacting object moves away from the right conditions. Temporary clocks are not strange in astronomy. A supernova remnant changes over time. A comet returns until its path changes or its material is exhausted. A young star may flare often during one stage and quiet down later. QPS may also be transient. Some may appear, repeat for a time, and then stop. That possibility makes catching them even more important. If we do not watch at the right time, the alarm may have rung and gone silent before we knew it existed. There is another subtlety in the alarm clock image. A clock does not only mark time, it tells you something about the mechanism inside. A pendulum clock reveals the swing of the pendulum, a quartz watch reveals the vibration of a crystal, an atomic clock reveals transitions in atoms. A QPE, if we can understand it, may reveal the motion of matter in one of the most extreme gravitational environments available to observation. The repetition is not just a curiosity. It is a probe. It may let us infer the size of the orbit, the mass of the black hole, the structure of the accretion disk, or the way gas responds when hit, heated, or compressed. This is why astronomers care so much about the spacing between eruptions. Suppose the waiting time is 9 hours. That does not automatically tell us the orbit is 9 hours because the geometry may be more complicated. An object might cross the disk twice per orbit, or one crossing might be brighter than the other, or the disk might be tilted. Or relativistic precession might shift the crossing points. Still, the recurrence time narrows the possibilities. It sets a scale. A process that naturally takes years is unlikely to explain eruptions separated by hours. A process happening very close to the black hole becomes more plausible. The duration matters too. If the flare lasts about an hour, then whatever produces it must release energy and cool or fade on that timescale. The rise time tells us how quickly the emitting region turns on. The decay tells us how it loses energy. The colour of the X-ray light, meaning its energy distribution rather than a colour our eyes could see, tells us about temperature. If the spectrum softens or hardens during an eruption, that gives another clue. A cosmic alarm clock does not simply ring. It rings with a tone, a volume, a length, and a pattern. All of those details carry information. There is a pleasant irony here. Black holes are famous for hiding things. The event horizon hides whatever crosses it. The central object itself gives us no direct light, and yet the environment around a black hole can become extraordinarily informative. It is like trying to understand a person who never speaks, but who keeps rearranging the furniture very loudly in the next room. We cannot see inside the horizon, but we can study the gas outside. We can watch how the accretion disk brightens. We can measure the timing of eruptions. We can infer what invisible objects may be moving there from the effects they produce. That is especially useful in galactic centres because they are crowded places. The central black hole is surrounded by stars, stellar remnants, gas clouds, magnetic fields, and debris from past interactions. Objects can be placed onto unusual orbits. Stars can be nudged inward. Compact remnants can sink over time through gravitational interactions. A small object may end up circling the central black hole in what astronomers call an extreme mass ratio system, because one body is vastly more massive than the other. These systems are difficult to see directly, but if the smaller object interacts with gas, it may announce itself through repeated flares. This is where QPS become more than strange X-ray flashes. They may be signposts for hidden populations of compact objects near supermassive black holes. If some QPS are caused by stars or stellar remnants orbiting close to central black holes, then finding more QPS could tell us how common such orbits are. That matters for gravitational wave astronomy, because small compact objects spiraling into massive black holes are expected to produce gravitational waves that future space-based detectors may be able to measure. Light and gravity could become two ways of studying the same kind of system. One telescope sees the X-ray alarm. Another future instrument may feel the space-time vibration of the moving object itself. Still, we should not get too far ahead of the evidence. It is tempting, when a pattern appears, to choose the most exciting explanation and invite it in for tea. Science has to be a little stricter than that. Every model has to reproduce the observed timing, the flare duration, the temperature, the luminosity, the long-term evolution, and the host galaxy environment. It must explain not only one source, but the growing family of sources, including those that behave differently. Some QPEs are faster, some are slower, some have stronger bursts, some appear after known tidal disruption events, others appear in newly active galactic nuclei. The alarm clocks are not all built the same way, or at least they are not all set to the same hour. That diversity is useful. If all QPEs looked identical, one model might fit neatly. Because they differ, astronomers can compare them. A system with eruptions every few hours may point to one scale. A A system with eruptions every few days may point to another. A source that brightened optically years before its X-ray eruptions may suggest a changing accretion environment. A source that was quiet and then woke up may suggest a black hole beginning to feed. Differences help separate ingredients. They show what changes when the black hole mass changes, when the disk changes, when the orbit changes, or when the supply of gas changes. From the listener's side, it may help to imagine a set of clocks in a strange workshop. One ticks quickly, one rings every few hours, one waits days between chimes, one has a clean tone, another rattles as if something inside is loose. You would not assume they all had the same internal design, but you would still recognize that they belong to the same broad family. They are all devices that turn hidden motion into sound. QPS may be doing something similar with X-rays. They turn hidden motion near black holes into repeating light. The phrase cosmic alarm clock also carries a small emotional trick. Alarms are familiar, black holes are not. By placing them together, we make the extreme feel approachable. That is not the same as making it less strange. A QPE is still a high-energy eruption from near a supermassive black hole in another galaxy. It still involves physics that stretches our intuition, but the rhythm gives us a handle. We understand waiting for a signal. We understand noticing that something happens again. We understand being startled by repetition. The universe may be vast, but a repeated pattern is something the human mind naturally follows. That may be one reason these events feel so compelling. They are not just bright, they are timed. They give the impression of a process with memory. The system seems to know, in a physical sense, how to return to eruption. Of course it does not know anything. Gas has no plan. Gravity keeps no diary. The black hole is not deciding to flare before lunch, but physical systems can behave predictably without intention. An orbit returns because motion and gravity require it. A disk instability repeats because matter crosses a threshold. A resonance can build because two cycles line up. The rhythm is not conscious, it is lawful. And this is where the alarm clock comparison becomes deeper than a joke. A clock is useful because it transforms a regular physical process into a signal we can read. In a mechanical clock, gears translate motion into hands moving around a face. In a QPE, gravity and gas translate an unseen process into X-ray bursts. The telescope reads the signal, the astronomer reads the telescope, and slowly the hidden machinery becomes less hidden. As we drift farther into the subject, it is worth keeping the scale in mind. These eruptions are not happening across the whole galaxy. They are coming from the very centre, from a region tiny compared with the galaxy itself. A galaxy may contain hundreds of billions of stars. Its disk or halo may stretch across tens or hundreds of thousands of light years. The QPE source is tied to the central black hole environment, a region that may be only light hours or light days across depending on the details. From across the universe, the telescope cannot resolve that region as a detailed picture. It sees the combined light. Timing becomes the microscope. That is a beautiful idea in a practical way. When we cannot see something directly, we can sometimes measure how it changes. If an object is too small on the sky to image, its variability can still reveal its size. A region cannot change coherently faster than light can cross it, so rapid changes imply compact regions. A flare that rises quickly must come from a place small enough for the signal to coordinate over that time. In this way, a light curve becomes a ruler. The clock becomes a map. So when a QPE rises and falls over about an hour, and returns after hours or days, those timescales are not just notes in a logbook. They are physical constraints. They say the source is compact. They say the process is close to the black hole. They say the system is dynamic in a way we can watch. That is why a seemingly simple repeated flash can carry so much meaning. It is not just that the light came back, it is that the timing of its return points inward, toward the deep gravitational well where matter moves fast, heat builds quickly, and orbits can be bent by relativity. Near the end of an ordinary day, when your own alarm is perhaps set for morning, It is strange to think that far away another kind of alarm is ringing in X-rays. Not for waking, not for warning, not for anyone really. It is simply the visible sign of matter obeying extreme rules. Yet because we are here, because we have built instruments and placed them above the atmosphere, because we have learned to count photons and compare patterns, that distant ringing becomes part of human knowledge. A black hole flares, and somewhere on Earth a scientist updates a plot. The universe acts, we make a graph. It is a humble arrangement, but a very effective one. From the outside, a galaxy can look peaceful in a way that is almost misleading. It may sit in a telescope image as a soft blur, a pale oval, a small smudge of starlight among thousands of others. Nothing about it seems to shout. No bright jet slices out from the centre. No obvious explosion dominates the view. No dramatic spiral arm points a helpful arrow toward the mystery. It is simply there, a distant island of stars looking calm enough that you might pass over it while searching for something more spectacular. But galaxies are very good at keeping secrets. At the centre of most large galaxies, and probably many smaller ones too, there is a supermassive black hole. In some galaxies, that black hole is actively feeding. Gas falls inward, heats up, and the centre shines brightly across the electromagnetic spectrum. Those galaxies are called active galactic nuclei, or AGN, and some of them are so bright that the centre can outshine the combined starlight of the entire galaxy. They are the loud ones. They are the cosmic cities with every window lit and someone apparently operating heavy machinery at midnight. Other galaxies seem quiet. Their central black holes are still there, but they are not obviously feeding, or if they are feeding, the meal is faint, thin, and hard to detect. The stars continue orbiting. The galaxy continues existing. From far away, nothing much appears to be happening. It is a little like walking past a dark house and assuming everyone inside is asleep, only to later discover that someone in the basement has been building a very complicated clock. QPEs often bring our attention to these quieter places. That is one of the reasons they are so interesting. They do not always appear in the most obvious blazing energetic galactic centres. Some have been found in galaxies that looked relatively inactive, or at least not wildly active, until X-ray observations revealed a repeating pulse. That is important because it suggests that the black hole's surroundings may be doing something subtle and temporary, rather than simply belonging to a long-running bright active nucleus. The galaxy may look calm in visible light. While close to the central black hole, a small region of hot gas is rising and fading in X-rays on a schedule only a space telescope can see. This difference between what a galaxy seems to be and what its centre is doing is one of the quiet pleasures of astronomy. A galaxy image gives us one kind of truth. Timing gives us another. In visible light, you see the stars, the shape, the general glow, the long history of star formation and structure. In X-rays, you may see the hot, compact, high-energy behaviour near the black hole. These two views do not always tell the same story at first glance. A galaxy can look ordinary and still have something very strange happening in its middle. That is because the region producing a QPE is tiny compared with a galaxy. A galaxy can stretch across tens of thousands of light years. Its stars are scattered across an enormous volume. Its outer edges are so vast that light itself needs many human civilizations' worth of time to cross them. But the action near a QPE may be happening in a region only light hours or light days across, close to the central black hole. From our distance, we cannot separate that tiny region into a neat picture. We cannot zoom in until we see the disk, the orbiting object, the splashing gas, or whatever is driving the eruptions. We see the combined light, and the clue is not shape. The clue is change. This is why a hidden pulse matters so much. A pulse is not about the galaxy's appearance. It is about its behaviour over time. If you take one image, the galaxy may seem unremarkable. If you watch in X-rays, you may find that the centre brightens, fades, and brightens again. The pulse was not painted across the galaxy for everyone to see. It was tucked into the timing of high-energy photons, arriving from the centre like tiny knocks from a locked room. The word quiet can also be a little slippery in astronomy. A quiet galaxy is not truly quiet. It still contains stars, it still has gas, dust, stellar remnants, planets, magnetic fields, and perhaps a central black hole slowly interacting with its surroundings. Quiet usually means that the central black hole is not producing the kind of strong, steady activity we associate with bright AGN. It means the galaxy does not immediately announce itself as a feeding black hole system. The silence is comparative. It is the difference between a calm kitchen and a kitchen where someone has placed a saucepan on every burner and then left the room. This matters because black holes need fuel to shine. If there is no gas close enough to heat and fall inward, the black hole can remain nearly invisible. It may be enormous, but mass alone does not make it bright. A supermassive black hole sitting in a clean environment can be dark, patient, and difficult to notice. Give it gas, though, even a small supply, and the region outside the event horizon can become luminous. The gas does not fall straight in. It forms a disk or stream. It collides with itself. It loses energy. It heats. In the inner regions, the temperatures can become high enough to produce X-rays. So when a quiet galaxy develops an X-ray pulse, the first practical question is not only why the pulse repeats, it is also where the fuel came from. One possibility is that a star wandered too close. Galactic centres are crowded, and over long stretches of time, stellar orbits can be nudged by gravitational interactions. A star that once circled safely may find itself placed on a dangerous path. If it passes too near the central black hole, the difference in gravity across the star can pull it apart. This is a tidal disruption event. Some of the star's material may be flung outward. Some may wrap around the black hole and become a temporary accretion flow. That fresh gas could awaken a black hole that previously looked quiet. If later eruptions occur from that new flow, the galaxy may seem to have developed a heartbeat after years of stillness. Another possibility is that the black hole was already being fed at a low level, but the feeding was too faint or too cool to stand out strongly. Then something changed. A disk might have shifted into a different state. A compact object might have begun crossing it. A stream of gas might have reached the inner region. A small change near a black hole can have visible consequences, because the inner accretion flow is an efficient place to turn motion into radiation. Matter close to the event horizon is moving fast, and when it heats, it can shine intensely. The whole galaxy does not need to change. Only a small central zone needs to become active. This is one of the important lessons hidden inside QPEs. A galaxy's centre can change on timescales far shorter than the galaxy itself. The outer galaxy may look almost frozen across a human lifetime, but the black hole environment can change in hours, days, months, or years. That contrast is striking. The galaxy is ancient and broad. The eruption is compact and quick. The stars drift through their long orbits, while deep in the middle, the X-ray light may rise and fall before a person has finished a night's sleep. The case of SDSS 1335+0728, nicknamed Ansky, is a useful example of this kind of surprise. For years, it was an unremarkable galaxy. Then, in late 2019, its brightness began to increase. Astronomers started following it with different observatories, trying to understand whether they were seeing the black hole switch on. Later, X-ray observations showed powerful, repeated eruptions, unlike the more modest QPEs first known from other systems. This does not mean every quiet galaxy is about to reveal such a pulse, but it shows how a central black hole can move from apparent calm into activity within a human observing window. For astronomers, that is a rare gift. It is one thing to infer that galaxies evolve. It is another to watch a black hole wake up while the data are still arriving. There is something almost domestic about the phrase "wake up." though the reality is not domestic at all. A black hole does not wake like a person. It does not stretch, make coffee, and reconsider its schedule. What changes is the supply and behavior of matter around it. Gas reaches the inner region. A disk forms or brightens. Radiation increases. The galaxy's center, once dim, becomes active. Still, the phrase helps because from our point of view the change is real. A source that was quiet is no longer quiet. The house is dark, then a window glows. In QPE sources that glow is not steady. It pulses. This pulsing can make a quiet galaxy feel almost alive, though again we should keep the science clean. No intention is involved. No signal is being sent to us. The eruptions are not messages, they are physical events. But living things often have rhythms, and the human mind naturally recognizes rhythm. A heartbeat, breathing, sleep cycles, footsteps in a hallway. When we see light rising and falling from a galactic center, it is hard not to use words like pulse, even though the mechanism is gas and gravity rather than muscle and blood. The pulse is hidden because ordinary vision cannot see it. If you could look at one of these galaxies through a powerful optical telescope, you might see its starlight, perhaps its central region, perhaps signs of dust or structure. But the QPE itself is most clearly detected in X-rays. These X-rays come from gas heated to extreme temperatures near the black hole. Our eyes are not built for that. Ground-based telescopes cannot easily catch cosmic X-rays because the atmosphere absorbs them. So the hidden pulse is hidden twice. First by scale, because it comes from a tiny central region, and second by wavelength, because it shines in light our eyes cannot see and our atmosphere blocks. Space telescopes turn that hidden pulse into data. They sit above the atmosphere and count X-ray photons. Each photon is tiny, but together they build a record. Over time, the record becomes a light curve. The galaxy's center may look like a point source, but the brightness of that point changes. It rises, it falls, it waits. The telescope does not need to see the disk directly. It can measure the rhythm. This is similar to how doctors can learn from a pulse without seeing the heart directly. A pulse does not show every chamber or valve. It does not reveal the whole anatomy. But it tells you that something is moving in a repeated way. It tells you about timing, strength, and regularity. A QPE light curve does something comparable for a galactic nucleus. It does not show every detail of the central engine, but it tells us that a compact region is repeatedly releasing energy. That is enough to begin asking sharper questions. The host galaxy also gives context. Its size, stellar population, central black hole mass, and previous activity all matter. Many known QPE sources appear to involve relatively low-mass supermassive black holes, often around hundreds of thousands to a few million solar masses, rather than the billion solar mass giants found in the brightest quasars. This may be important because the timescales near a black hole depend on mass. Around a larger black hole, the same kind of orbital or disk process may take longer. Around a smaller supermassive black hole, the inner region is smaller and the clock can tick faster. So the hidden pulse may be easiest to see in certain kinds of galactic centers, where the black hole mass, gas supply, and observational timescale line up in a convenient way. Convenient, of course, is a word astronomers use cautiously. The universe is not trying to make its secrets easy. QPEs are rare in current catalogues, partly because they may truly be rare, and partly because they are easy to miss. To find one, you need to observe the right galaxy in X-rays for long enough to catch the flare. A short observation might land between eruptions and see only the quiet state. A survey might pass over the source too quickly. A flare might happen while the telescope is looking somewhere else. The pulse may be there, but unless you listen at the right time, you hear silence. This creates a selection problem. The QPEs we know are the ones we were lucky enough or careful enough to catch. There may be more hidden in archival data. There may be many that appeared and faded before anyone observed them properly. There may be galaxies that pulse only for a temporary phase, then return to quiet. That possibility makes the known examples feel a little like fireflies seen through a distant forest. You glimpse one flash, then another, and you know there may be more in the dark than you can count. The phrase, previously quiescent, appears often in discussions of QPEs, and it is worth unpacking gently. Quiescent means quiet or inactive. In this context, it often refers to a galactic nucleus that did not show strong signs of ongoing black hole activity before the eruptions were detected. That does not mean absolutely nothing was happening. It means the galaxy was not known as a bright, active nucleus in the usual way. Then X-ray bursts were found, and the centre had to be reconsidered. A galaxy once placed in the mental folder marked ordinary might suddenly need a new label. That is one reason QPRs are not just about black holes, they're also about discovery. They remind us that our categories are based on what we've observed so far. A quiet galaxy may not be quiet forever. A faint nucleus may enter a temporary active phase. A central black hole may receive a fresh supply of gas. A hidden object may disturb a disk. The universe is not static simply because our earlier data were calm. There is also an important human side to this. Modern astronomy depends heavily on revisiting a source is discovered. Scientists search older surveys. They compare optical images from years earlier. They check X-ray archives. They look at ultraviolet data. They ask whether the galaxy changed before anyone noticed the X-ray pulse. This is how a quiet galaxy gains a history. The hidden pulse is not only a present observation, it becomes a clue that sends researchers backward through records, looking for the first signs of awakening. Sometimes, the earlier signs are subtle. A galaxy may brighten in optical light before X-ray eruptions appear. That could suggest that material began moving inward, or that the accretion flow changed over time. Other times, the X-ray behaviour may be the first clear alert. Either way, the timeline matters. If we know when the galaxy was quiet, when it brightened, when the eruptions began, and how they changed, we can test models. A disk instability model may predict one kind of evolution. An orbiting object model may predict another. A tidal disruption-related model may require a particular sequence of events. The hidden pulse is not isolated, it sits inside a story. The quiet galaxy also helps with contrast. If a bright AGN flickers, it may be difficult to separate the QPE from all the other activity. The central region is already noisy. There may be jets, winds, broad emission lines, variable disks, and complicated X-ray spectra. In a quieter galaxy, a repeating X-ray eruption can stand out more clearly. The background is dimmer. The pulse is easier to recognize. It is like hearing a small clock in a silent room rather than in a train station. That does not mean quiet systems are simple. A faint black hole environment can still be physically complicated. The disk may be newly formed, warped, tilted, or unstable. The gas supply may be patchy. The central star cluster may contain compact objects moving on unusual orbits. The black hole mass may be uncertain. Dust may obscure some wavelengths. Each source has its own complications, but the lack of overwhelming pre-existing activity gives the eruptions room to be noticed. As we imagine one of these galaxies, it helps to keep both scales in mind at once. On the large scale, there is the galaxy itself, a wide system of stars moving slowly under gravity. Its light has travelled for millions of years. Its shape may look steady. On the small scale, at the centre, there is the black hole environment. Gas may orbit in minutes or hours. An object may cross the disk. The X-ray light may flare and fade while the rest of the galaxy appears unchanged. The contrast is almost like a sleeping body with one tiny nerve firing repeatedly. The whole form seems still, but deep inside there is a signal. That signal is not loud to us. By the time the photons reach Earth, they are sparse. The telescope gathers them patiently. The data may look modest before analysis, but the meaning is large. A hidden pulse from a quiet galaxy tells us that black hole feeding can begin or change in ways we're only starting to understand. It suggests that the boundary between inactive and active galactic nuclei may not be as clean as a simple label. It shows that small central regions can reveal themselves through timing even when images look ordinary. It also reminds us that black holes are part of galactic ecosystems. They do not exist in isolation. Stars can wander close, gas can fall inward, past events can leave debris, compact remnants can orbit in the dark. The central black hole shapes its surroundings, and the surroundings feed back into the black hole's behaviour. A QPE may be a brief visible sign of that relationship. Not the whole relationship, but one bright pulse from within it. For the viewer settling into the story, this is a useful place to slow down. A distant galaxy looks quiet. At its heart is a black hole. Around that black hole, a small amount of matter has become hot enough to shine in X-rays. For reasons still being tested, that hot region does not simply glow steadily. It brightens, fades, and brightens again. The rest of the galaxy keeps its calm face. The pulse remains hidden unless the right instrument is watching. There is no need to imagine the entire galaxy shaking or flashing like a warning beacon. The stars do not all respond. The spiral arms, if it has them, do not flare. The event is central, compact, and high energy. That makes it more mysterious in some ways. A small region near the black hole is producing a pattern visible across immense distances, while the vast galaxy around it acts almost like a quiet frame around a tiny moving hand. As more QPE sources are found, astronomers will compare their host galaxies carefully. Are they mostly low-mass galaxies? Do their central black holes share similar masses? Are they recently awakened nuclei? Do they show signs of past tidal disruption events? Are their stellar populations unusual? Do they live in environments where stars are more easily pushed toward the centre? These are not side questions. They may help explain why the pulse exists at all. The black hole is central, but the galaxy provides the setting. For now, the quiet galaxy with a hidden pulse gives us a way to enter the mechanism without rushing. We have a place, a galactic centre. We have a source, a supermassive black hole environment. We have a signal, repeating X-ray eruptions, and we have the central problem. Something near the black hole is turning a hidden process into a visible rhythm, while the surrounding galaxy remains outwardly calm. That calm is what makes the pulse feel sharper. A bright quasar roaring across the universe is impressive, but it is not surprising that a quasar is active. A quiet galaxy that begins to flash in X-rays is different. It feels like a whisper becoming a metronome. It asks us to look again at places we might have dismissed as ordinary. It reminds us that a galaxy can keep a secret at its centre for years, decades, or longer, until one telescope happens to be watching when the hidden clock begins to ring. To find the source of the pulse, we have to be careful about one simple idea that is easy to say and very easy to picture incorrectly. A black hole does not erupt from the inside. Nothing bright climbs out from beneath the event horizon. Nothing crosses that boundary, changes its mind, and comes back carrying a lantern. The darkness at the centre keeps what falls in. So when astronomers speak of a black hole eruption, they're really speaking about the matter just outside it. The gas, dust, plasma, and possibly broken remains of a star that have not yet crossed the point of no return. That may sound like a small distinction, but it changes the whole picture. The black hole is not a volcano with fire bursting from a crater. It is more like an invisible drain surrounded by water moving so fast that the water heats, churns, splashes and glows before it disappears. The bright part is not the hole. The bright part is the crowded, heated, restless material still orbiting outside. In QPEs, that material seems to brighten in soft X-rays again and again, giving us the repeated pulse we have been following. Soft X-rays are still energetic light. The word soft does not mean gentle in the bedtime sense, and it certainly does not mean safe to hold in your hand. It simply means lower energy X-rays compared with harder X-rays. They are produced by very hot gas, often in the range of hundreds of thousands to millions of degrees. depending on the exact system and model. When this kind of emission rises sharply from the centre of a galaxy, astronomers know they are looking at something compact and extremely hot. When it fades and then rises again, they know the hot region is not just changing once. It is being rebuilt, reheated, disturbed, or refilled. So what actually erupts near the edge of darkness? The most practical answer is hot gas. More specifically, plasma in the black hole's immediate environment changes its brightness, temperature, or emitting area in a way that produces a burst of X-rays. Plasma is gas so hot or energetic that electrons are separated from atoms, leaving charged particles moving through magnetic fields and radiation. It is not rare in the universe. Stars are plasma. The solar wind is plasma. Much of the ordinary matter we can observe beyond planets is plasma. Near a black hole, though, plasma is placed under extreme conditions. Gravity pulls it inward. Rotation spreads it into a disk. Friction and magnetic turbulence heat it. Radiation escapes, if it is still outside the event horizon, and that escaping radiation becomes our clue. There is a helpful everyday comparison, though it should not be taken too literally. Imagine stirring honey around the bottom of a bowl. The honey moves slowly because it is thick. Now imagine that the bowl is spinning. The honey is hotter than a star's atmosphere, and the middle of the bowl is a one-way opening in space-time. That is still not quite an accretion disk, but it at least gives us the feeling that matter near a black hole does not fall quietly. It has angular momentum, meaning it wants to keep circling. Before it can fall inward, it has to lose some of that orbital motion. As it does, different layers of gas rub, twist, and interact. Energy that was once orbital motion becomes heat and light. In a QPE, some part of this heated flow seems to change rapidly. The X-ray brightness can increase by a large amount during an eruption. In GSN 069, for example, the X-ray count rate rose dramatically during bursts, and the events lasted roughly an hour before settling back down. That does not mean the entire disk suddenly appears and disappears. It means the region responsible for the observed X-rays becomes much brighter, hotter, larger, or some combination of those things. The details matter because different models predict different kinds of changes. One simple version would be a heating event. Something injects energy into a region of gas close to the black hole. The gas heats up, shines more strongly in X-rays, and then cools or expands. The flare fades. Later, the process happens again. If you have ever watched a burner on an electric stove glow, dim, and glow again as the thermostat cycles, you have a very domestic version of repeated heating. Near a black hole, the thermostat is not a small knob with numbers on it, and the stove should not be used for pancakes, but the idea of energy building and releasing is a useful first step. Another version involves a physical impact. If a star or compact object orbits on a path that takes it through the accretion disk, then each crossing could disturb the gas. The object would not need to crash into the black hole. It would pass through the disk, pushing material aside, creating shocks, heating gas, and possibly lifting some of it above and below the disk. That disturbed gas could then radiate in X-rays. The object continues its orbit. The disk begins to settle. After one orbital cycle, or perhaps half a cycle if it crosses the disk twice, the object plunges through again. Another disturbance, another flare, another ring of the cosmic alarm. This impact picture is one reason people often describe QPEs with language that sounds almost mechanical. The orbit provides the timing, the disk provides the material, the crossing provides the eruption. It is not difficult to imagine a small object repeatedly punching through a glowing disk like a bead passing through a sheet of mist. But the real situation is more complicated. The disk may be thick or thin. It may be tilted. It may be warped. The orbit may precess, shifting its orientation because of strong gravity near the black hole. The object may lose energy, change its path, or strip material from itself. The disk may not respond the same way every time. This is one reason the eruptions are quasi-periodic rather than perfectly periodic. The same general act may repeat, while the exact details change. If the object is a normal star, the story becomes especially dramatic. A star passing close to a supermassive black hole can lose gas from its outer layers. It may survive for a while, but each close approach can remove more material. If it crosses a disk, it can also create a shock and leave behind heated gas. If the star is dense enough or the orbit not too destructive, it might keep returning. But there are limits. Too close, and the star is torn apart. Too much stripping, and it cannot survive many passages. Astronomers therefore have to ask whether a proposed star can live long enough to explain the observed sequence of eruptions. A compact object changes the problem. A white dwarf, neutron star or stellar mass black hole is much smaller and denser than an ordinary star. It can survive stronger tidal forces. It can orbit closer to the central black hole without being immediately destroyed, though the environment is still harsh. If such an object moves through the accretion disk, it may produce repeated disturbances while remaining mostly intact. A stellar mass black hole would be dark by itself, but its gravity could plough through the disk and create shocks in the gas. A neutron star or white dwarf might also disturb the disk and perhaps lose or collect material. These possibilities are appealing because they place a durable clock hand near the supermassive black hole, moving through the same region again and again. Yet the disk instability idea remains important. In that picture, nothing has to strike the disk from outside. The eruption comes from the disk's own changing state. Gas in accretion disks can be unstable because its temperature, pressure, opacity, magnetic fields, and flow of angular momentum are all connected. A small change can push part of the disk into a hotter state. Matter may move inward more quickly. The X-ray emission rises, then the local supply drains or cools, and the system returns to a lower state. After matter builds up again, another flare occurs. This kind of repeating release is familiar in some other accreting systems such as dwarf novae, though QPEs happen in a very different setting and at much higher energies. The challenge is that QPEs can be very sharp and high amplitude. The eruptions may look too distinct for some simple disk cycle models. Their host galaxies may not always look like standard active galactic nuclei. In some cases, the disk may be linked to a recent tidal disruption event rather than a long-lived AGN disk. Also, if a disk was present before QPEs began, why did the eruption start only later? That question has become especially important in studies of sources like GS N069, where long-term observations suggest a complex history. Models have to explain not only the bursts themselves, but also why they appear during some phases and not others. This is where tidal disruption debris enters the room, perhaps a little untidily, as debris often does. When a star is torn apart by a supermassive black hole, its gas does not all fall in at once. Some escapes, some remains bound. Some form streams that collide and circularize, gradually creating a disk. This material can feed the black hole for months, years, or longer. If QPS appear after such an event, then the erupting gas may be part of the stellar remains. In that case, what erupts is not just ordinary gas that happened to be near the black hole. It may be the heated leftovers of a star that wandered too close and became part of a temporary accretion flow. That sounds grim, but it is also one of the ways the universe makes observable light. A star in a dangerous orbit becomes fuel. Its material forms a disk. The disk shines. If another object moves through the disk, or if the disk becomes unstable, repeated X-ray eruptions can appear. The original star may be gone, partly gone, or transformed into a smaller surviving core depending on the details. The black hole's environment then becomes a place where past destruction produces present rhythm. Still, we should not picture the eruption as a neat blob of gas being thrown outward like a cannonball. In many models, the X-ray flare is radiation from heated material, not necessarily a large amount of matter being launched away from the black hole. Some gas may expand. Some may be blown into an outflow, some may fall inward, some may settle back. Observations of certain systems, including GSN 069, have even found evidence for highly ionized outflowing material, suggesting that gas can be driven away from the central region during or around the active phase. But the main observed QPE signal is light, not a photograph of matter exploding. The eruption is seen as a rapid increase in X-ray emission from a compact region. This difference matters because the word eruption can make us think of volcanoes. A volcano throws material upward because pressure builds beneath a surface. A QPE is not that kind of eruption. There is no solid crust around the black hole. There is no mountain. There is no magma chamber. There is hot plasma under gravity, and when conditions change, that plasma emits much more X-ray light. The word eruption is useful because the brightness rises suddenly and dramatically. It is less useful if it makes us imagine the black hole spitting things out from inside itself. The light comes from outside, from matter still visible to the universe. The edge of darkness, then, is not the event horizon alone. It's also the region just outside where matter is still accessible to observation, but already under the black hole's control. In this region, gravity has not yet hidden everything, but it has changed everything. Orbits are fast, tidal forces are strong, energy release can be enormous. Gas close to the black hole has a much deeper gravitational well to fall through than gas near an ordinary star. As it spirals inward, it can convert a large fraction of its gravitational energy into radiation. This is why accretion onto black holes can be so bright. A black hole may be dark, but feeding one can light up a galaxy's centre. The inner accretion flow may also have different zones. Farther out, the disk may be cooler and shine more in optical or ultraviolet light. Closer in, the gas may become hot enough for X-rays. Above the disk there may be a corona, a region of very energetic particles that can scatter lower energy photons into X-rays. In some systems, winds may rise from the disk. Magnetic fields may thread the gas. The exact geometry in QPEs is still being studied, but it is likely not a simple flat pancake glowing evenly from edge to edge. It may be layered, warped, patchy, and changing. When the QPE occurs, the X-ray emitting part seems to grow more active. In some observations, the spectrum changes during the flare, meaning the distribution of X-ray energies shifts. That tells astronomers the temperature or structure of the emitting region is changing. If the flare were only a dimming and brightening of a fixed lamp, the spectrum might remain the same, but QPEs often show spectral evolution, so the physical state of the gas itself is changing. It is as if the lamp not only gets brighter, but also changes from a warm glow to a hotter white, and then cools again, though again in X-rays rather than colours we can see. The size of the emitting region is constrained by time. If the light rises quickly, the region cannot be too large, because changes cannot coordinate across a space faster than light can travel. An hour-long flare points to a compact region, at least by galactic standards. That compactness pulls our attention inward toward the black hole. It tells us we are not watching a galaxy-wide event. We are watching something close to the centre, close enough that the black hole mass and the orbital timescales of the inner disk matter. Here, the term gravitational radius becomes useful, though we do not need to lean on it too heavily. Astronomers often measure distances near black holes in units tied to the black hole's mass. The larger the black hole, the larger its natural scale. Around a black hole of a few 100,000 solar masses, the region where matter can orbit on hour-like timescales is relatively close in. Around a much larger black hole, similar processes would stretch to longer times. This is why known QPEs are often discussed in connection with lower-mass supermassive black holes. Their inner clocks can tick at timescales we can observe conveniently, like hours rather than months. Convenient for us at least. For the gas, there is probably nothing convenient about it. Imagine material moving in a disk around a black hole hundreds of thousands of times more massive than the Sun. The inner gas is hot enough to emit X-rays. It may be struck by an orbiting object, squeezed by magnetic turbulence, or driven through a rapid thermal change. It brightens, releasing energy that travels away as photons. Some of those photons cross intergalactic space. A few eventually reach a telescope near Earth. They are counted. The count rate rises on a graph. And from that line we infer the violence of a place we cannot visit. There is something wonderfully indirect about this. We do not see the eruption with our eyes. We do not see the disk in detail. We do not see the object that may be causing the pulse. We do not see the event horizon. We see X-ray light and the timing of that light, and from it we build a physical story. Astronomy often works like that. It is not guessing in the casual sense. It is inference from measurement. The universe gives us light. We compare that light to physics. We remove explanations that fail. We keep those that survive, at least for now. The for now is important, because QPEs are still new enough that models are evolving quickly. A discovery can favour one idea. A later observation can complicate it. A new source can behave in a way no one expected. This is not a problem. It is how the subject grows. Early explanations are tested against better data. Some break, some are repaired. Some merge with others. The erupting material remains the same physical reality, but our description of it becomes more precise. A useful way to picture the whole thing is to imagine 3 layers. At the centre is the black hole, dark and unreachable once matter crosses the horizon. Around it is the immediate environment, where gas forms a hot disk or flow. Moving through or within that environment may be an object, instability, or stream that sets the rhythm. The eruption we observe is the disk or gas responding. It is the middle layer lighting up. The black hole provides the gravity, but the gas provides the glow. This is why saying the black hole erupted is a convenient shorthand, not a literal description. It is like saying the city woke up when really millions of individual people turned on lights, opened doors, started engines, and made coffee. The city did not wake as one creature. The phrase is still useful because it describes the change we notice from outside. In the same way the black hole system erupts, the central region brightens, the X-ray signal rises, but the physical light is coming from matter outside the horizon. When we ask what erupts near the edge of darkness, the answer points us toward the accretion disk again and again. The accretion disk is not just scenery around the black hole. It is not a decorative ring placed there so the artist's impression looks more dramatic, though to be fair it usually does. The disk is where most of the visible action happens. It is the place where matter changes from cold drifting material into something hot, bright, fast, and measurable. It is the place where gravity turns motion into heat. And in the strange case of quasi-periodic eruptions, it may be the surface, the fuel, the timing device, or perhaps all 3. An accretion disk forms because matter almost never falls straight into a black hole. That may seem surprising at first. In simple drawings, gravity is often shown as a funnel, and objects roll down into the middle as if the universe were a smooth bowl. But real matter has motion of its own. A gas cloud near a black hole may be moving sideways. Debris from a torn star may be stretched into long streams. Material drifting through the centre of a galaxy may carry angular momentum, which is just a careful way of saying it has spin or sideways motion that keeps it from dropping directly inward. So instead of plunging straight into the dark centre, the gas circles. It spreads out. It forms a flattened, rotating flow around the black hole. That flow is the accretion disk. You can imagine it as a glowing dinner plate in space if dinner were served at several million degrees and the middle of the plate were a one-way door into darkness. The comparison is not perfect, but it is useful. The disk is wide and flat compared with its thickness. It circles the black hole. Its inner edge reaches close to the event horizon, while its outer regions may extend much farther away. The material in the disk is not solid. It is gas and plasma, moving in rings, streams, eddies, and turbulent patches. Each part orbits at a different speed. The inner gas moves faster, the outer gas moves more slowly. That difference in motion is one of the reasons the disk heats up. If every ring of gas moved together perfectly, with no friction, no turbulence, and no magnetic effects, the disk would be much duller and much less useful to astronomers. But accretion disks are not polite skating rinks. They are messy. Different layers interact. Magnetic fields thread through the plasma. Turbulence helps move angular momentum outward, allowing some material to drift inward. As gas loses orbital energy and moves closer to the black hole, that energy has to go somewhere. A large part of it becomes heat. Hot gas radiates. Near a black hole, the radiation can include ultraviolet light and X-rays, which are the signals we use to study the inner region. That is why the disk glows. Not because the black hole itself is shining, but because matter is being forced to give up energy as it approaches. In a way, the disk is a kind of cosmic receipt. It records the cost of falling inward. The deeper the gravitational well, the more energy can be released. Black holes are extraordinarily efficient at this when matter forms a disk around them. A star shines by nuclear fusion in its core, slowly converting mass into energy. An accretion disk shines because gravity and motion are being turned into heat and radiation. It is not gentle, but it is extremely effective. For QPEs, the disk matters because the bursts appear in X-rays, which means something close to the black hole is heating or brightening rapidly. In many models, the disk is the material that actually erupts in brightness. If an object crosses it, the disk is struck. If an instability grows, the disk is where conditions change. If tidal disruption debris feeds the black hole, the disk may be made from the torn star's remains. The black hole supplies the gravity, but the disk supplies the visible response. Without gas outside the event horizon, there would be no X-ray flare for our telescopes to catch. The alarm would have no bell. The inner part of the disk is especially important. Far from the black hole, gas may be cooler and slower. It may shine at lower energies. Close in, the orbital speeds rise, the gravitational energy available is greater, and the temperatures can become high enough to produce X-rays. In a QPE, the repeated flare is thought to come from this compact hot region, not from the entire broad disk at once. The disk may be large compared with the event horizon, but the erupting zone is likely small compared with the galaxy. That is why the brightness can change quickly. A huge region across light years could not rise and fall in an hour as one coherent source. A compact region near the black hole can. A useful way to picture the disk is to imagine a record spinning on a turntable, though we have to repair the image immediately because a real accretion disk is not rigid like a vinyl record. The inner parts orbit faster than the outer parts. The whole thing is fluid. It may be warped, it may be tilted, it may be thick in some regions and thinner in others. It may have streams feeding it unevenly. The gas is charged, which means magnetic fields matter, and because the black hole bends space-time near its center, the motion of gas close in does not follow the simple, tidy orbits we might expect from schoolbook gravity. So, yes, a record is a starting image. But then the record becomes boiling, magnetic, stretched, and partially invisible. Not something you would want to play music on, unless your taste in music is very extreme. The disk's structure depends on how much matter is flowing through it. If the black hole is being fed heavily, the disk can be bright and active. If the supply is weak, the disk may be faint, thin, or even hard to detect. In a newly awakened galactic center, the disk might be forming from fresh material. In a tidal disruption event, the disk may begin as a stream of stellar debris that slowly collides with itself and settles into a more circular flow. In an older active galaxy, the disk may already exist before any QPE-like behavior begins. These different histories may produce different kinds of eruptions, which is one reason astronomers do not assume that every QPE is made in exactly the same way. Now, if the accretion disk is our glowing dinner plate, the QPE is not the whole plate suddenly catching fire from edge to edge. It is more likely a change in part of the plate, especially the inner region. Perhaps a patch of gas heats rapidly. Perhaps material is lifted out of the disk by a collision. Perhaps a wave of increased accretion moves inward. Perhaps the disk's inner edge changes shape or temperature. The observed X-ray flare is what happens when that change becomes bright enough for our instruments to notice. The disk may remain present before, during, and after the flare, but its inner emission rises dramatically for a short time. This is different from a simple explosion. In an explosion, we often imagine material being thrown outward in all directions and then fading as it expands. In a QPE, some gas may move outward, and some models do include expanding clouds or outflows, but the central issue is repeated X-ray brightening. The disk does not need to vanish and reform from nothing each time. More likely, it is being disturbed, heated, or cycled through a brighter state. The eruption is a change in radiation from matter that is already trapped in the black hole's neighborhood. The disk can also act like a measuring surface. If a compact object passes through it, the disk gives that object something to hit. Without the disk, an orbiting object might circle silently in the dark, producing little light. With the disk, each crossing can create a visible event. The object plunges through gas. Gas is shocked and heated. A bright region forms. X-rays increase. Then the gas cools, expands, or falls inward, and the flare fades. The object continues around its orbit and returns. In this picture, the disk is like the surface of a pond, and the object is something repeatedly dipping through it. You do not see the object directly. You see the ripples and splashes. The pond image is helpful, though again the real disk is far stranger. A pond has a calm surface because gravity points downward and water rests in a shallow basin. An accretion disk is held in orbit by gravity, rotating around a black hole, and the surface may not be sharply defined. The gas is hot and ionized. Magnetic fields can lift material above the disk. Radiation pressure may push on it. A compact object crossing the disk may not make a neat splash, but a shock-heated plume, a wake, or a hot bubble of gas that later radiates. Still, the idea of a repeated disturbance gives us a way to understand why a disk could turn hidden motion into visible light. The thickness of the disk matters. A thin disk is easier for an object to cross quickly, perhaps producing a shorter flare. A thicker disk may create a longer interaction. A tilted disk may produce crossings that are uneven. A warped disk might explain why flares are not identical from one cycle to the next. If the orbiting object crosses the disk at different radii, or if the disk itself changes between passages, the eruption can vary. This helps explain the quasi in quasi-periodic. The underlying orbit may be regular, but the disk is not a perfectly repeatable target. There is also the question of how fast the disk can recover. If something disturbs it, the gas does not instantly return to its previous state. It may take time for the heated region to cool, for material to settle, for the inner flow to refill, or for turbulence to spread the energy. The waiting time between QPEs may therefore reflect not only the orbit of a companion, but also the disk's own response. A flare could depend on whether enough gas is accumulated in the right place before the next crossing. If the object returns too soon, the disk may not be ready to produce the same bright burst. If it returns later, the gas may have rebuilt. This kind of interaction can make a natural clock that is regular but not perfectly exact. Some models suggest that repeated impacts can create expanding clouds of hot gas above the disk. These clouds may shine in X-rays as they expand and cool. Others suggest that the impact drives shocks through the disk, heating material at the crossing point. Still others focus on changes in the inner accretion flow, where the rate at which matter reaches the black hole rises and falls. At the moment, no single picture has settled every case, but the disk remains central because it is the most obvious reservoir of hot matter available to shine. In systems linked to tidal disruption events, the disk may be especially unusual. When a star is torn apart, its debris does not immediately become a smooth, well-behaved disk. The streams of gas can be long, eccentric, and messy. They may collide with themselves. They may form a disk gradually. The orientation of that disk may be misaligned with the orbit of other material. It may be thick in some places, uneven in density, and changing over time as the supply of fallback material decreases. If QPEs occur in such an environment, the disk is not a stable dinner plate set neatly on the table. It is more like dinner arriving during turbulence, which is rarely ideal. This may sound complicated, and it is, but it also gives astronomers many clues. The flare duration can tell us about the size and cooling time of the emitting gas. The recurrence time can tell us about orbital or disk timescales. The X-ray temperature can tell us how hot the emitting region becomes. Changes over months or years can show whether the disk is evolving. If the eruptions become weaker, farther apart, or disappear, that may mean the gas supply is fading or the geometry has changed. If they grow stronger, perhaps the disk is becoming denser, hotter, or more favourable for producing X-rays. Each flare is a small experiment run by nature under conditions we could never create in a laboratory. The black hole mass sets the scale of the whole stage. Around a smaller supermassive black hole, the inner disk is physically smaller and the orbital timescales are shorter. Around a larger black hole, similar processes can take longer. Many known QPE systems appear to involve relatively modest supermassive black holes, at least compared with the enormous giants powering the brightest quasars. This may help explain why their eruptions repeat on timescales of hours or days rather than centuries. The disk's clock is tied to the black hole's mass, just as the size of a clock's gears affects how quickly its hands move. But unlike a mechanical clock, an accretion disk is not built from solid parts. It is a flow. It is constantly exchanging energy and angular momentum. Its magnetic fields can grow, tangle, and reconnect. Its gas can become unstable. Radiation can push on it. Gravity from a companion object can disturb it. Strong relativity can twist the motion close to the black hole. This makes it hard to predict exactly, but it also means the disk can produce rich behaviour. A rigid machine might only tick. A disk can flicker, flare, pulse, wobble, and change over time. It is less tidy but much more interesting. The glow of the disk also tells us why black holes can be detected at all. A lonely black hole with no nearby matter is almost invisible. It bends light from background stars, perhaps. It affects orbits if something is close enough. But it does not shine. Give it a disk, and suddenly the dark object becomes surrounded by evidence. The disk is like a signpost around something that refuses to be seen directly. In QPEs, that signpost is not steady. It blinks. It pulses. It gives us timing information, which may be even more valuable than a still image. This is one reason the dinner plate metaphor works gently. A plate reveals the meal. It holds the material in a shape we can recognize. It shows where something has been placed, moved, or disturbed. If something taps the plate, you may hear it. If something spills across it, you may see the pattern. The accretion disk around a black hole holds the gas in a structure where physical processes become visible. It is not just matter falling in. It is matter arranged by gravity into a form that can record disturbance. Imagine then one of these QPE systems during its quiet interval. The disk is still there, or at least the inner gas flow is still present. It may be glowing faintly in X-rays. The telescope records a lower count rate. Near the black hole, gas continues to orbit. Magnetic turbulence continues to stir. If a companion object is involved, it continues along its path, moving through curved space-time around the central mass. Nothing in the system is truly still. The quiet interval is only quiet compared with the flare. Then conditions line up. Perhaps the companion reaches the disk. Perhaps gas has built up in the inner flow. Perhaps a thermal instability crosses a threshold. The disk responds, a region heats, X-rays rise, the light curve climbs. For a short time, the hidden central engine becomes brighter, and across space, photons begin a long journey to our detectors. The flare fades, but the disk does not forget in a human sense. Physically, it has changed. Gas has moved. Energy has been released. The next eruption will happen in a disk slightly different from the one before. That small difference is important. It means each flare is both a repeat and a new event. The system returns to a similar condition, but not an identical one. That is true of many natural cycles. Your own breathing repeats, but no two breaths are exactly the same. Ocean waves repeat, but each wave has its own shape. A kettle boils each morning, but the bubbles are not arranged identically. QPEs may be regular because a driving process repeats, and irregular because the disk is a living flow of physics rather than a rigid clock face. Not living in the biological sense, of course. The disk is not alive, but it is active, responsive, and changing. If astronomers could resolve the disk directly, they might see structures that would make the models much clearer. They might see a warped ring, a hot spot, an impact plume, or a stream feeding the inner region. But these galaxies are too far away, and the relevant scales are far too small. So instead, the disk speaks through timing and spectrum. The light curve tells when the disk brightens. The X-ray spectrum tells how hot the emitting material is. Longer-term monitoring tells whether the pattern evolves. The disk is not drawn for us in detail. It is inferred piece by piece from the way it glows. This can feel indirect, but it is one of astronomy's strengths. We learned the composition of stars long before we could ever touch stellar material, by reading their spectra. We find exoplanets by watching stars dim slightly, or wobble under gravity. We infer dark matter from the motions of galaxies and the bending of light. QPEs fit into that same tradition. We cannot see the disk's inner structure clearly, but we can watch its brightness rise and fall. We can learn from the repeated glow. If something is causing the flare by crossing the disk, what is that something? If a companion object is orbiting close to the black hole, how did it get there? Could it be a surviving star, a dense stellar remnant, or a small black hole moving around a much larger one? How can an unseen object announce itself only through the disk it disturbs? Somewhere inside that glowing disk, or moving through it on a tight and dangerous path, there may be a second object. Not the central black hole itself, but a much smaller companion, circling in the deep gravitational field like a tiny hand sweeping around a clock face. Tiny, of course, is a very flexible word when black holes are involved. The companion might still be a star. It might be the dense leftover core of a dead star. It might even be a smaller black hole with several times the mass of the Sun. Compared with the supermassive black hole in the centre, though, it is small enough to be treated almost like a bead moving around a cannonball. If the cannonball weighed hundreds of thousands or millions of suns, and the bead could punch holes in a disk of X-ray hot gas. This possible companion is one of the most interesting ideas in the study of quasi-periodic eruptions, because it gives the repeating flare a natural timer. A disk by itself can change, certainly. Gas can become unstable. Heat can build. Matter can move inward in bursts, but an orbiting object gives the system something that returns. It moves around the black hole. It reaches a certain point in its orbit. It interacts with the disk. A flare appears. Then it continues onward, leaving the disturbed gas to cool, expand, settle, or fall inward. After the orbit carries it back again, the process can repeat. The result is not a perfect metronome, but it can be regular enough for astronomers to see a pattern in the X-ray light. The idea is simple at the surface, which is why it is so attractive. If you want a repeated signal, look for a repeated motion. Orbits are one of nature's most reliable ways to make repeated motion. Earth returns around the Sun. The Moon returns around Earth. binary stars swing around each other, pulsars flash as they rotate. So when a black hole system produces repeating X-ray eruptions, an orbiting companion is an obvious suspect. Not proven, not alone in the lineup, but definitely standing there looking suspicious. The companion would not be visible directly. These galaxies are too far away, and the region near the black hole is too small on the sky. Even if the object is a star, its light would be completely overwhelmed by the surrounding galaxy and by the high energy emission near the black hole. If it is a neutron star or a small black hole, it may produce little or no visible light of its own. What astronomers look for instead is the effect it has on the disk. The companion's presence is inferred from the timing and shape of the eruptions. It is like knowing someone is walking upstairs because you hear the floorboards creak, not because you can see their feet. If the companion's orbit is tilted relative to the disk, it may pass through the disk once or twice per orbit. Imagine a small object moving around the central black hole on a path that cuts through a flat sheet of gas. Each time it crosses the sheet, it disturbs the material. Gas is compressed. Shocks can form. A hot region appears. The X-ray brightness rises. Then the disturbed gas changes, cools, spreads, or is pulled along by the flow, and the flare fades. If there are 2 crossings per orbit, there may be 2 opportunities for eruptions. If one crossing is stronger than the other, the light curve may show alternating strong and weak flares. If only one crossing produces enough X-rays to detect, then we may see 1 flare per orbit even if the object crosses the disk twice. That last detail matters because real systems rarely behave like classroom diagrams. A simple drawing might show the object passing through a disk at 2 neat points, producing 2 identical flashes. But near a black hole, nothing is that tidy. The disk may be denser on one side than another. The companion may hit the disk at different angles. The first crossing may disturb the gas so much that the second crossing happens through a changed environment. Strong gravity may rotate the orbit over time, so the crossing points shift. If the companion is a star, it may lose material. If it is a compact object, it may gravitationally focus gas around it. The same orbit can produce different flares because the target is not the same each time. A normal star is the easiest companion to imagine. Stars are common in galactic centres, and gravity can place them on unusual orbits over long periods. A star passing close to a supermassive black hole may survive if it does not come too close. If its orbit takes it through an accretion disk, its outer layers can plough through the gas. That collision can heat disk material, create a wake, and possibly strip gas from the star itself. In this picture, the star is like a swimmer repeatedly crossing a very hot stream, though the stream is orbiting a black hole, and the swimmer is risking a rather permanent inconvenience. The difficulty is survival. A star close to a supermassive black hole is subject to tidal forces, meaning the black hole's gravity pulls more strongly on the near side of the star than on the far side. If the difference becomes too large, the star can be stretched and torn apart. That is the tidal disruption process we have mentioned before. A star producing QPEs by repeated passages must therefore be close enough to disturb the disk and create X-rays, but not so close that it is destroyed immediately. It must also survive repeated disk crossings, which can strip material from it and slow its orbit. That is a narrow and demanding arrangement. The universe does make narrow arrangements, but scientists have to check whether they last long enough to explain what we observe. A white dwarf is another possible companion in some models. This is the dense core left behind after a sun-like star has ended its normal life. A white dwarf packs a star's worth of material into an object roughly the size of Earth. It is much denser than an ordinary star, which means it can survive stronger tidal forces. It may orbit closer to the black hole without being torn apart as easily. If it passes close enough, it might lose small amounts of material over repeated orbits, or interact with a disk in a way that produces recurring flares. The white dwarf idea is appealing for some low-mass supermassive black holes, especially when the timescales are short and the orbit must be tight. But it has its own challenges, including how the white dwarf arrived on that orbit and how long the system can keep producing visible eruptions. A neutron star would be even denser. It is the collapsed core of a massive star, with more mass than the Sun squeezed into a sphere about the size of a city. A neutron star can survive extremely strong gravity, though it is not invincible. Near a supermassive black hole, it could move through the disk and disturb the gas without being torn apart in the way an ordinary star would. But neutron stars are rare compared with normal stars, and detecting their role indirectly is difficult. If one is involved, its presence might be revealed through the timing, the energy of the flare, or perhaps, in the long future of observational astronomy, through gravitational waves as it slowly spirals inward. Then there is the possibility of a stellar mass black hole. This would be a black hole formed from the collapse of a massive star, much smaller than the central supermassive black hole, but still a strong gravitational object in its own right. A stellar mass black hole crossing an accretion disk would not have a surface to collide in the ordinary sense. Instead, its gravity would pull and focus disk gas around it. It could create shocks, heat the gas, and stir the disk as it passes. Since it is compact and hard to destroy, it could survive many orbits. It would be almost completely invisible except for the disturbance it causes. This makes it a very interesting candidate, because it could act like a hidden needle repeatedly passing through a glowing cloth. Systems like this, where a small compact object orbits a much larger black hole, are called extreme mass ratio systems. The phrase sounds technical, but it means exactly what it says. One object is extremely massive compared with the other. A supermassive black hole may weigh 1 million suns. A companion may weigh 1 sun, 10 suns, or perhaps a little more. The ratio is enormous. In such a system, the small object's orbit is shaped almost entirely by the central black hole. It moves through curved space-time, and over long time scales it may gradually lose energy and spiral inward. If there is gas in the disk, collisions or drag can also change the orbit. If gravitational waves are produced, they carry away energy too. The companion is not simply circling forever in a perfect loop. Its path may be slowly evolving. That slow evolution may leave marks in the QPE timing. If the orbit shrinks, the eruptions might arrive slightly closer together over time. If the disk precesses, the crossing points may change, altering the flare pattern. If the companion's orbit precesses because of general relativity, the timing may shift in a more complicated way. These changes can be small, but repeated observations may reveal them. This is where the alarm clock idea becomes more useful again. A clock that slowly changes its ticking rate tells you something is happening inside. A QPE whose recurrence time drifts may be telling us that the companion's orbit, the disk, or both are changing. In ordinary life, if your alarm rings earlier each morning without you changing the setting, you might suspect a fault, or perhaps a very rude piece of technology. In a black hole system, a changing interval is not a fault, it is a measurement. It can reveal orbital decay, disk evolution, or precession. A stable pattern tells one story, a drifting pattern tells another. Scientists compare the predicted timing from different models to the observed light curves, looking for the arrangement that best reproduces the data. The companion is invisible, but its schedule may give it away. This is especially important because the companion model can connect QPEs to gravitational wave sources. A compact object orbiting a supermassive black hole is exactly the kind of system future space-based gravitational wave detectors are designed to study, if the object is dense enough and the orbit becomes tight enough. The X-ray eruptions may appear during a phase when the compact object is interacting with gas. The gravitational waves would come from the motion of the masses through space-time. Light tells us about the disk and the hot gas. Gravitational waves would tell us about the orbit itself. One system could, in principle, speak in 2 different languages. For now, that remains a future possibility. But it is one reason QPEs have attracted so much attention. They may be signposts pointing to hidden compact objects deep in galactic centres. There is also a question of how the companion got there. Galactic centres are crowded, but they are also vast compared with the size of the central black hole. A star or compact object does not simply decide to settle into a tight orbit near the event horizon. Something must place it there. Gravitational encounters with other stars can scatter objects onto new paths. A binary system may be disrupted by the supermassive black hole, leaving one star captured and another ejected. A compact object may gradually sink inward through interactions with surrounding stars. A tidal disruption event may create a disk that later reveals a companion already present. Different formation paths predict different kinds of orbits. Some produce highly eccentric paths, long narrow loops that bring the companion close to the black hole only briefly. Others produce more circular orbits, where the companion stays near the same distance as it circles. The shape of the orbit matters for QPS. A highly eccentric orbit could produce brief, intense interactions near closest approach, with long waits between them. A more circular orbit crossing the disk repeatedly could produce more regular eruptions. If the orbit is tilted, the disk crossings may happen at specific points. If the disk is itself tilted or warped, the geometry becomes richer. The flare timing is therefore a map of motion, not a complete map, but one with enough landmarks to be useful. It is worth remembering that the companion does not have to be large to have a large effect. Near a supermassive black hole, the disk gas is already moving fast and holding enormous energy. A small disturbance can change how that energy is released. A companion crossing the disk is not supplying all the flare energy from its own body. It is triggering or shaping the release of energy from the gas. This is similar to how a small spark can set off a much larger fire if fuel is already present. Though in QPEs the fuel is hot accreting plasma rather than dry wood, and the fire is X-ray radiation rather than something you could warm your hands by. Please do not try to warm your hands by a quasi-periodic eruption. It is several galaxies away and has poor safety standards. The disk's response depends on its density and temperature. A dense disk gives the companion more material to disturb, potentially producing a brighter flare. A thinner disk may produce a weaker signal. A hotter disk may radiate differently from a cooler one. If the disk was created by a tidal disruption event, its density may decline over years as the supply of stellar debris fades. That could cause QPE amplitudes to decrease over time. If the disk becomes more settled, the flare shapes may change. If the companion loses energy through disk crossings, the orbit may shrink, changing the recurrence time. The companion and disk are not separate performers taking turns. They interact, and each interaction can alter the conditions for the next one. This is why scientists do not simply ask, "What is the companion?" They ask, "What companion, on what orbit, crossing what disk, around what black hole, at what stage of disk evolution?" It is a longer question, less catchy perhaps, but more honest. A main sequence star in a dense, fresh disk may behave differently from a stellar mass black hole in a thin, older disk. A white dwarf on an eccentric orbit may produce a different pattern from a compact object on a nearly circular one. The same label, QPE, may cover more than one physical arrangement. The shared feature is the repeated X-ray flare. The machinery beneath may vary. Still, the companion model has a strong appeal because it turns the quasi-periodic timing into something physical and intuitive. A hidden object returns. It stirs the disk. The disk glows. The object moves on. The disk cools. The object returns again. That image gives us a way to understand why the flares happen more than once, without requiring the disk to spontaneously choose the same moment again and again. It is not proof, but it is a good working picture. Imagine watching a pot of thick soup from above. If it bubbles once, that could happen for many reasons. If a spoon dips into it every few seconds from just out of view, you would see a repeated disturbance. You may not see the spoon directly, but the surface would tell you it is there. In a QPE system, the disk is the surface. The companion is the unseen spoon. The X-ray flare is the hot splash. The comparison is not exact, and the soup would need to be replaced with plasma in strong gravity. But it gives the mind something firm to hold while the physics becomes more detailed. There is another subtle point. If the companion is moving through the disk, it may not only create light, it may also remove or redistribute angular momentum. It may drag on the gas, it may carve a path or create waves, it may excite spiral structures in the disk. These changes can feed matter inward, leading to enhanced accretion onto the black hole. In that case, the flare might not be only the local heated splash at the crossing point. It might also include extra radiation from gas driven inward after the disturbance. This would make the timing more complex. The impact happens at one moment, but the brightest X-ray emission may occur after gas has responded and moved. A small delay between crossing and flare could carry information about disk physics. The companion may also change the disk's vertical structure. When an object passes through a disk, it can lift material above and below the disk plane. This material may expand into a cloud, radiate as it cools, and then fall back or escape. Some models of QPEs focus on these expanding clouds as the source of the X-ray emission. The flare shape then depends on how quickly the cloud expands, how dense it is, how hot it becomes, and how the radiation escapes. That is very different from a model where the flare is mainly caused by a sudden increase in accretion at the inner edge. Both can involve a companion, but they place the bright emission in different parts of the system. This is why more observations matter. If the flare spectrum changes in a certain way, it may favour an expanding hot cloud. If the timing follows orbital decay, it may favour a companion crossing the disk. If the eruption strength tracks the long-term fading of a tidal disruption disk, that may support a post-disruption origin. If the recurrence time stays extremely stable, that may tell us something about the orbit. If it shifts, that may tell us something else. A companion model is not one fixed answer. It is a family of answers that must be narrowed by data. There is also the matter of inclination, which simply means the angle at which we view the system, and the angle between the orbit and the disk. If we see the disk more face-on, the light may look different than if we see it edge-on. If the companion crosses the disk at a shallow angle, it spends more time ploughing through gas. If it crosses steeply, the interaction is quicker. A shallow crossing might produce a longer or brighter flare. A steep crossing might produce a sharper one. These geometrical details can shape the observed light curve without changing the basic ingredients. Near a black hole, even the orbit itself can be strange. General relativity predicts that close orbits do not close perfectly like simple ellipses. The closest point of approach can shift each time around. This is called precession. Around the Sun, Mercury's orbit precesses by a tiny amount, and that tiny amount helped confirm Einstein's theory. Near a supermassive black hole, precession can be much stronger. For a QPE companion, precession could alter where and when the object crosses the disk. It could make the eruption timing drift. It could create patterns that look complicated at first, but become meaningful when modelled with relativity. The tiny companion, if it exists, is not merely stirring the fire. It is moving through curved space-time while doing it. That thought brings the scale back into focus. We may be discussing a star or small black hole, something tiny compared with the central mass, but it is operating in one of the most extreme settings in astrophysics. It may orbit at distances where speeds are enormous and gravitational effects are strong. It may interact with gas hot enough to shine in X-rays. It may slowly lose energy and move inward. It may be part of a system that someday, far in the future, or perhaps in some cases not too far by cosmic standards, ends with the companion crossing the event horizon. The QPE phase could be a temporary interval before that final inspiral, a time when the small object is still outside, still returning, still disturbing the disk enough for us to notice. There is something quietly remarkable about the fact that we can discuss such a hidden object at all. We have not photographed it. We have not weighed it directly. We have not watched it move against the stars. We infer it from repeated X-ray flares in distant galactic centers. The data are indirect, but not weak. Timing can be powerful. A repeated signal can reveal an orbit. A changing interval can reveal evolution. A flare shape can reveal the disk's response. This is how astronomy often turns darkness into knowledge. It watches what the darkness does to nearby light. The companion, then, is not just an extra character in the story. It may be the reason the story repeats. Without it, the disk may still glow, but perhaps not pulse in the same way. Without the disk, the companion may orbit unseen. Together they create a signal. The supermassive black hole holds the system together with gravity. The disk provides fuel and radiation. The companion provides disturbance and timing. The X-ray telescope receives the result. Each piece matters. As more QPEs are found, astronomers will keep asking whether each one needs such a companion. Some may, others may not. Disk instabilities may still explain certain sources. A newly accreting black hole may produce eruptions through internal cycles. But the tiny companion remains one of the most compelling possibilities, because it links the repeating flare to a clear physical motion. It also opens a path towards studying objects we otherwise could not see near supermassive black holes. Every eruption might be a marker of an unseen orbit, a small body tracing loops through a place where gravity is too strong for ordinary intuition. For now, we can picture the system in a calm and careful way. At the centre sits the supermassive black hole, dark and massive. Around it, the accretion disk glows with hot gas. Moving through this disk may be a smaller object on a tight orbit. Each time it returns to the right place, it disturbs the gas. The disk responds with a burst of X-rays. The flare travels outward, leaving the galaxy, crossing space, and eventually reaching a detector built by people on a small planet who were curious enough to look. The companion stays hidden, but the fire it stirs is visible. If a companion is really acting as the clock hand, why is the timing not perfectly regular? Why do the eruptions come back with a rhythm, yet still shift enough to earn the name quasi-periodic? A quasi-periodic eruption is not perfectly periodic. It does not behave like a laboratory clock ticking at exact intervals under carefully controlled conditions. It repeats, but it drifts. It follows a pattern, but the pattern is not rigid. One eruption may arrive slightly earlier than expected. Another may come late. One flare may be brighter, another weaker. One may rise quickly, while the next takes a little longer to reach its peak. The signal is regular enough that astronomers can see a rhythm, but irregular enough that the rhythm itself becomes part of the mystery. This is not a flaw in the observation. It is information. If the eruptions were perfectly timed forever, that would suggest a very stable mechanical driver, something like a clean orbit producing the same event under the same conditions again and again. But QPE systems are not clean machines. They are made from hot gas, strong gravity, magnetic fields, radiation, possible stellar debris, and perhaps a companion object moving through a disk that changes every time it is disturbed. So the timing is almost regular because something repeats, and not quite regular because the repeating process happens inside a messy physical environment. A simple way to picture it is to think of footsteps through snow. If someone walks in a straight line at a steady pace, the footprints will be roughly evenly spaced. But if the snow is deeper in some places, or the ground slopes, or the person slips slightly, the spacing changes. You can still tell that one walker made the trail. You can still follow the direction. But the footprints are not stamped by a machine. QPEs are like that. The repeated flares may trace the motion of a companion or the cycling of a disk, but each flare happens in conditions that are a little different from the last. The accretion disk is one of the main reasons for this imperfection. A disk around a black hole is not a solid surface. It is not a smooth dinner plate that stays exactly the same between taps. It is a flow of plasma. It has density variations, temperature changes, turbulence, magnetic structures, and perhaps winds rising from it. If a companion crosses the disk, it does not strike the same disk twice in exactly the same state. The first crossing heats the gas and may lift some material out of the disk. It may change the local density. It may launch a shock. It may drive matter inward or push it outward. By the time the companion returns, the disk has recovered only partly, or recovered in a different shape, or not recovered at all in the region being crossed. This matters for the timing as well as the brightness. If the disk must rebuild or cool before it can produce a strong eruption, then the arrival of the companion is not the only clock. The disk has its own response time. A companion might return after a fixed orbital interval, but the flare it produces could depend on whether enough gas is present, whether the gas has reached the right temperature, or whether the previous disturbance left the region depleted. In that case, the orbital motion provides the repeated opportunity, while the disk decides how strongly and perhaps how quickly the system responds. It is a little like someone knocking at a door every hour, but the doorbell only rings properly when the wiring has cooled down from the last time. Not ideal home maintenance, but very useful astrophysics. The orbit itself may also be less simple than it first appears. Around a normal star or planet, we often picture orbits as closed ellipses, repeating the same path again and again. That picture works well in many everyday astronomical situations, but near a supermassive black hole, especially close enough to produce hour-scale or day-scale eruptions, general relativity becomes important. The orbit may precess, meaning its closest point shifts each time around. Instead of tracing the same loop again and again, the companion's path slowly rotates. If that path intersects the disk, the crossing point can move. One passage may happen through a denser part of the disk, another may cut through a thinner region. One may occur closer to the black hole, where the gas is hotter and faster. Another may happen slightly farther out, where the response is different. This can make the eruptions look almost clock-like, but not exact. The companion still returns, the disk is still struck, but the geometry changes. The timing between the brightest moments may drift, because the place where the flare is produced is shifting. The flare may also change shape because the companion crosses the disk at a different angle or speed relative to the local gas. Near a black hole, even small changes in radius can matter, because orbital speeds and temperatures change quickly as you move inward. The system does not need to be wildly chaotic to produce noticeable differences. A slight shift in a very extreme environment can be enough. If the black hole is spinning, another effect can enter. A rotating black hole drags spacetime around with it, an effect called frame dragging. This can make tilted orbits and disks precess. You do not need to picture spacetime as a physical substance being stirred like soup, but the effect is real in the mathematics of general relativity. Motion near a spinning black hole is influenced by the black hole's rotation. If a disk is tilted relative to the black hole's spin, or if a companion's orbit is tilted relative to the disk, the geometry can evolve. That evolution can modulate the timing of the eruptions. The clock hand is not moving over a flat, fixed face. The face itself may be twisting. There is also the possibility that the companion's orbit is slowly changing size. If the companion loses energy, it can spiral inward. Energy can be lost through gravitational waves, through interactions with the disk, or through repeated drag as it passes through gas. Each disk crossing can act a little like moving through a thick fluid. The companion pushes gas aside, heats it, and loses some orbital energy in the process. Over many passages that can alter the orbit. If the orbit shrinks, the recurrence time may change. Depending on the details, the eruptions could come closer together, farther apart, or vary in a more complicated way. The timing drift then becomes a record of orbital evolution. This is why astronomers look not only at one or two flares, but at long monitoring campaigns. A few eruptions can reveal that a source is quasi-periodic. Many eruptions over months or years can reveal whether the pattern is stable, drifting, wobbling, fading, or changing in cycles. In some QPE sources, the timing has been difficult to fit with the simplest models. That does not mean the models are useless. It means the system may have more moving parts than the first version allowed. A companion may still be involved, but the disk may be precessing, changing density, cooling over time, or evolving after a past tidal disruption event. A disk instability may still be involved, but it may be driven or shaped by something orbiting through the gas. A tidal disruption event can make the timing especially complicated. If the disk formed from the debris of a star that was torn apart, then the disk is not a permanent steady structure. It is changing as the debris supply declines. The density may decrease over time, the disk may become thinner, its temperature may change, its inner region may settle gradually. If a companion is crossing this disk, then each passage occurs through a disk at a different stage of evolution. Early on, there may be more gas producing stronger flares. Later, the disk may thin out, producing weaker flares, or changing the time it takes for the gas to respond. This can make the QPE rhythm evolve over years. The flare amplitudes can also affect how the timing is measured. An eruption does not begin and end with a sharp bell ring. It rises from a lower state, reaches a peak, and fades. If one flare is bright and broad, its peak may be easier to identify. If another is weaker or irregular, the exact peak time can be harder to define. Telescope coverage also matters. If an observation begins after the flare has already started, or ends before it fully fades, scientists may have to infer parts of the light curve. That can add uncertainty. The source may be genuinely irregular, the data may be incomplete, or both may be true. Astronomy is often the art of separating the universe's behaviour from the limits of our viewing schedule. That practical issue is worth pausing on. We sometimes talk about telescopes as if they simply watch whatever we need, whenever we need it. In reality, space telescopes are shared, scheduled, and constrained. They orbit Earth. They have visibility windows. They may not stare at one galaxy continuously for weeks. A QPE source can erupt while the telescope is pointed somewhere else. A gap in the data can hide a flare. A short observation can miss the quiet interval or catch only the peak. When scientists reconstruct the recurrence pattern, they must account for those gaps. A cosmic alarm clock is easier to understand if you never leave the room. Unfortunately, astronomers sometimes have to step out because the telescope has other appointments. Even with excellent coverage, the flares themselves may not be identical because the emitting gas changes during each event. Suppose a companion punches through the disk and drives out an expanding cloud of hot gas. The X-ray flare might come from that cloud as it expands and cools. The time of maximum brightness would depend on the cloud's density, temperature, expansion speed, and opacity. If the disk is denser during one crossing, the cloud may be more massive or hotter. If the crossing angle changes, the cloud may expand differently. If the companion passes through a thinner patch, the flare may peak sooner or fade faster. The companion can keep a reasonably steady orbit while the visible flare still arrives with small variations. If the eruption is caused by disk instability rather than a crossing companion, the timing can be quasi-periodic for a different reason. Many unstable systems have cycles, but the cycles are not perfectly exact. Matter builds up until it reaches a threshold. The threshold depends on temperature, density, magnetic fields, and radiation. Once the instability starts, gas moves inward or heats up, producing a flare. Then the inner region resets. The next cycle begins, but the build-up does not happen under identical conditions every time. The amount of incoming gas may vary. Magnetic turbulence may shift. The disk's previous flare may have left it in a slightly different state, so the interval repeats roughly, not precisely. It is like a kettle that whistles when it boils, except the amount of water, the flame, and the kettle itself are slightly different each time. Also, the kettle is around a black hole, which makes cleaning it a challenge. This kind of threshold behaviour is common in nature. Earthquakes, geysers, and certain stellar outbursts can show rough repetition without perfect timing. Stress builds, pressure accumulates, energy is released, the system resets. But because the build-up process is irregular, the release is irregular too. QPE errors may share some of this character if disk physics is the main driver. The repetition tells us there is a cycle. The imperfection tells us the cycle is natural, not mechanical. In many cases, the best explanation may involve both an orbit and a responsive disk. The companion sets the opportunity for eruptions, while the disk sets the flare's strength, shape, and perhaps the exact delay between crossing an X-ray peak. This mixed picture feels realistic because the central region is not made from independent parts. The companion disturbs the disk. The disk's drag changes the companion's orbit. The black hole's gravity shapes both. Radiation from the inner flow affects the gas. If debris from a torn star is feeding the disk, the whole environment evolves over time. The quasi-periodic signal may be the combined result of all these interactions, not a single clean clock ticking alone in a vacuum. This is why the word clockwork should be used with a small smile. It is helpful, but it is not exact. A QPE is clock-like because it repeats. It is not clock-like because its gears are not rigid. Its gears are gas, gravity, and motion. The hands may be an unseen companion. The face may be a warped disk. The spring may be a supply of stellar debris. The bell is X-ray emission from hot plasma. Nothing about that will keep perfect time like a bedside clock from a reliable manufacturer. If it did, honestly, we might be more worried. There is also a deeper point about what scientists mean by periodicity. In observational astronomy, a signal can be called quasi-periodic if it has a preferred timescale, even when individual cycles vary. The system is not random. It has a rhythm, but the rhythm has width. It can be measured statistically rather than by a single fixed number. For QPEs, astronomers may discuss recurrence times, timing residuals, phase shifts, and changes in the interval between peaks. These are ways of describing how close the signal is to a perfect period and how it departs from one. The departures are not noise to be ignored, they are part of the source's behaviour. A timing residual is simply the difference between when a flare is expected and when it actually appears. If you predict a flare based on a simple period and it arrives 10 minutes late, that difference is the residual. Track those residuals over many eruptions and patterns may emerge. They may drift smoothly, they may oscillate, they may jump. Each pattern suggests a different physical cause. Smooth drift could hint at orbital evolution. An oscillating residual could point toward precession. Random scatter could indicate turbulence or variable disk response. This is how timing becomes a diagnostic tool. Not just, when did it happen? But, how did its lateness behave? That may sound amusingly specific, but it is powerful. A late flare can be a clue. An early flare can be a clue. A missing flare can be a clue too if the telescope was watching, and the source should have erupted but did not. Did the disk become too thin? Did the companion miss the dense region? Did the flare occur below detectability? Did the system enter a quieter phase? In some monitored QPE sources, eruptions have weakened or disappeared for a time, and then returned at lower luminosity or different temperature. That kind of behaviour tells us the engine is evolving, not simply ticking in place. The almost but not quite nature of QPEs therefore gives them scientific value. If they were random, they would be hard to connect to a stable mechanism. If they were perfectly periodic, they might be easier to model, but less informative about the messy disk around them. Because they are in between, they carry both structure and disturbance. The structure points to a repeating process. The disturbance reveals the conditions through which that process is moving. A simple clock on a wall hides its environment. It keeps ticking whether the room is quiet or noisy, warm or cool, at least within reason. A QPE does not hide its environment. The timing is shaped by the environment. The flare is shaped by the disk. The disk is shaped by the gas supply. The gas supply may be shaped by a torn star or a low-level feeding event. The orbit may be shaped by relativity and drag. So the irregularities are not a failure of the cosmic alarm. They are the alarm telling us about the room it is in. There is a calm way to hold this idea. The eruptions are not sloppy. They are physical. They are almost timed because a repeated driver exists. They are not perfectly timed because the driver is embedded in a changing system. That is true of many real rhythms. Your heartbeat is regular, but not perfectly spaced. Your breathing repeats, but changes with sleep, stress, movement, and rest. Ocean tides follow gravity's schedule, but local coastlines, winds, and weather shape the details. Natural rhythms often have a main beat and many small variations. QPEs may be a black hole version of that principle, though less suitable for meditation apps. As we watch these systems longer, the timing may reveal more than the eruptions themselves. It may help estimate the black hole's spin. It may constrain the disk's density profile. It may show whether the companion is spiraling inward. It may indicate whether the disk is precessing or thinning after a tidal disruption event. It may separate models that otherwise predict similar flare shapes. Timing is one of the few tools precise enough to probe a region too small and distant to image directly. That is why astronomers keep returning to these sources. One observation can catch an eruption. A sequence can reveal a period. Years of monitoring can reveal evolution. A QPE is not a single object frozen in a catalogue. It is a process unfolding over time. The more patiently we watch, the more the almost clock begins to show its inner workings. The small deviations, the late arrivals, the changing heights of the flares, the temporary disappearances, the returning pulses, all become pieces of the same puzzle. For our story, the important point is this. The eruptions repeat because some physical cycle near the black hole returns. They are imperfect because the cycle is moving through gas that changes, or through an orbit that shifts, or through a disk that evolves, or through all of those at once. The timing is neither random nor exact. It is a rhythm written by gravity into a messy disk of hot matter. To hear a black hole's heartbeat, first you have to listen in a kind of light your body was never built to sense. Human eyes are wonderfully useful for lamps, sunsets, book pages, and trying to find socks that somehow disappear beside the bed. But they cannot see X-rays. X-rays are too energetic for our eyes, and even if our eyes could detect them, Earth's atmosphere blocks most cosmic X-rays before they reach the ground. This is excellent news for living things. It is less convenient for astronomers who would very much like to know what hot gas around black holes is doing at 3 o'clock in the morning, so we put telescopes above the atmosphere. That may sound simple, but it is one of the quiet miracles behind this whole story. The repeating flare from a QPE does not arrive as a visible flash in the night sky. It does not twinkle between the stars. It does not give backyard observers a little wink through a small telescope. The signal comes mostly as X-ray photons, tiny packets of high-energy light that have travelled across space from a region close to a supermassive black hole. By the time they arrive near Earth, they are not a roaring wave. They are sparse, delicate arrivals, counted one by instruments that have to be cold, precise, patient, and placed in space where the atmosphere cannot swallow the message first. This is why X-ray observatories are so important to QPEs. Without them, the hidden pulse would stay hidden. The galaxy might still sit quietly in optical images. Its centre might not look especially dramatic. The stars would keep shining in visible light, and the black hole's strange repeated behaviour would go unnoticed. But above the atmosphere, an X-ray telescope can watch the galaxy's centre and record when the high-energy light rises and falls. It can turn invisible flickers into a measured rhythm. It can show us the black hole system not as a still image, but as a changing source with timing, temperature, and structure. The word hear is a metaphor here, but it is a useful one. Telescopes do not hear sound from space. Space is far too empty for ordinary sound waves to travel across it the way they travel through air. A black hole's heartbeat does not thump into a microphone, it arrives as light. But when scientists measure that light over time, the result can resemble listening. They're not only asking how bright the source is, they're asking when it brightens, how quickly it rises, how long it lasts, how fast it fades, and how soon it comes back. That is very close to taking a pulse. You place your fingers on a wrist and feel the timing. Astronomers place instruments in orbit and count photons. A single X-ray photon is not very informative by itself. It arrives, it is detected, and it adds one tiny mark to the record. But many photons together begin to make a pattern. The telescope records their arrival, times and energies. Over minutes and hours, the count rate changes. During a quiet interval, fewer photons arrive from the source. During an eruption, many more arrive. The brightness climbs, the detector notices, the light curve rises. Later the photon rate drops again, and the light curve falls. If another eruption follows, the pattern repeats. This is how the hidden heartbeat becomes a line on a graph. That line on a graph may look simple, but it is doing a lot of work. On one axis is time, on the other is brightness, or more precisely the number of X-ray photons detected over each interval. During a QPE, the line rises from the quieter level, reaches a peak, and then descends. Each eruption becomes a hill. Between eruptions, the graph settles into lower ground. A series of eruptions becomes a row of hills separated by valleys. Astronomers can measure the distance from one peak to the next, the width of each hill, the steepness of the rise, and the shape of the decline. The black hole system is not giving us a picture of itself directly. It is giving us a time signature. This is why long observations matter. If the telescope only looks briefly, it may catch nothing but the quiet state. That would not mean there is no QPE. It may simply mean the source was between eruptions. If the telescope catches only one flare, the event is interesting, but repetition remains uncertain. To identify a quasi-periodic eruption, scientists need to see the light return. Ideally, they want several eruptions because 2 flashes can suggest a pattern, but 3 or more begin to define it. More still let you test whether the timing drifts, whether the flare strength changes, and whether the system is evolving. Space telescopes have different strengths, and QPE studies often depend on combining them. XMM Newton is powerful for collecting X-rays because it has a large effective area, which means it can gather many photons from faint sources. More photons help build clearer light curves and better spectra. Chandra is famous for sharp X-ray imaging, which is useful when astronomers need to separate a source from nearby X-ray emission, or locate it precisely within a galaxy. NICER, mounted on the International Space Station, was designed for excellent X-ray timing, making it especially useful for tracking rapid changes in brightness. SWIFT can respond flexibly and monitor changing sources across different wavelengths, including X-rays and ultraviolet light. Each instrument listens a little differently, like a group of careful observers standing around the same quiet room, each noticing a different part of the sound. For QPEs, timing and energy both matter. Timing tells when the eruptions happen. Energy tells what kind of X-rays are arriving. A telescope does not merely count photons like coins in a jar, it can also measure their energies, creating a spectrum. In ordinary visible light, a spectrum tells us how much red, green, blue, and other colours are present. In X-rays, it tells us how the emission is distributed across different X-ray energies. That matters because the energy of the light is connected to the temperature and physical state of the gas. A hotter region tends to emit higher energy photons, a cooler one emits softer X-rays. If the spectrum changes during the flare, astronomers know that the gas is not merely becoming brighter. Its physical conditions are changing. This is one of the main ways X-ray telescopes move the story beyond something flashed. They can show that during an eruption, the source may become hotter, larger in emitting area, or both, depending on the model used to interpret the spectrum. They can compare the flare state with the quiet state. They can ask whether the emission looks like thermal radiation from hot gas, whether there are signs of absorption, whether winds or outflows are present, and whether the same pattern repeats in each burst. The light curve tells the heartbeat. The spectrum tells something about the blood if we keep the medical comparison just long enough and then let it go before it becomes too dramatic. There is another practical detail that makes X-ray timing delicate. Space telescopes need accurate clocks. If you're studying a source that changes over minutes or hours, the instrument must know precisely when each photon arrived. This is especially important when comparing observations from different telescopes. If XMM Newton sees an eruption and NISA follows up later, scientists need reliable timing to connect the records. If the source may erupt every few hours, an error in timing could confuse the pattern. Fortunately, modern observatories are designed with careful timekeeping, because high-energy astronomy often depends on knowing not only what arrived, but exactly when it arrived. It is fitting in a way that we study a cosmic clock with clocks on spacecraft. The QPE itself may be produced by an orbit, a disk cycle, or a companion repeatedly crossing gas near the black hole. The telescope watches with its own onboard timing system. Researchers then correct for the spacecraft's motion, Earth's motion, and the details of observation windows. The final light curve is the result of several layers of timekeeping. A black hole system pulses, a satellite records, a scientist aligns, the graph appears. Somewhere between the extreme gravity of a galactic center and a computer screen on Earth, a rhythm becomes readable. Observation windows can make the work challenging. A telescope may not be able to stare continuously at one source. Earth may block the target for part of an orbit. The spacecraft may pass through regions where the background radiation is high. Other scheduled observations may take priority. The source itself may erupt during a gap. This means the data are not always as complete as one would wish. Sometimes an eruption is caught from start to finish. Sometimes only the rising part is seen. Sometimes the telescope begins just after the peak, like someone entering a room after the kettle has already boiled, and everyone is pretending they did not hear it. Scientists then model the missing parts carefully, but they remain honest about uncertainty. Background noise is another issue. X-ray detectors do not receive only photons from the target. They can also detect particles and background X-rays from other sources or from the instrument environment. Astronomers have to subtract or account for this background. They compare the source region with nearby regions of the detector. They remove times when the background is high. They check that the flare is truly coming from the galaxy's center and not from a detector artifact or unrelated source. This careful cleaning is not glamorous, but it is essential. A black hole's heartbeat should not be confused with the telescope equivalent of a sneeze. Once the data are clean enough, the light curve can be folded, compared, and modelled. Folding is a technique used when scientists suspect a period. They take the data and stack cycles on top of each other according to a proposed recurrence time. If the eruptions line up, the period may be meaningful. If they do not, the timing may be more irregular, or the proposed period may be wrong. For QPEs, this can be tricky because the signal is quasi-periodic. It may not fold perfectly. That imperfection is not failure. It helps reveal how the system changes from flare to flare. Researchers also look at timing residuals, the differences between expected and observed flare times. Suppose you predict each eruption using a simple period. If one flare arrives early, another late, and another very late, those differences form a pattern of their own. They may hint at orbital precession, disk evolution, or changing geometry. In some QPE studies, timing residuals have become an important tool for testing whether an orbiting companion is plausible. The black hole system may not be keeping perfect time, but the way it fails to keep perfect time can be just as informative as the rhythm itself. There is a kind of patience in this work that suits the subject. Astronomers do not simply point once and declare the mystery solved. They return. They request more observations. They compare old data with new data. They check whether the eruptions have changed over months or years. They ask whether a source has faded below detectability or reappeared in a cooler, weaker state. They use X-ray telescopes as long-term listeners, not just cameras. The source may alter its behaviour, and that change becomes part of the evidence. Multi-wavelength observations help too, even though X-rays are central. Optical and ultraviolet telescopes can reveal whether the galaxy's nucleus has brightened at lower energies. Infrared data can show dust heated by radiation. Radio observations can search for jets or outflows. If a QPE source was preceded by a tidal disruption event, optical surveys may have recorded an earlier flare from the star being torn apart. If the black hole is waking up, optical brightness may change over years. The X-rays show the heartbeat close to the centre, but the rest of the spectrum can show how the larger environment responds. That said, X-rays remain the sharpest tool for the eruptions themselves. QPEs are defined by their X-ray behaviour. The bursts are strongest and clearest in that high-energy band. In some cases, ultraviolet observations do not show the same rapid variability as the X-rays, which tells scientists that the X-ray flare may come from a very compact hot region, while the ultraviolet emission may come from a broader disk that changes more slowly. This difference between wavelengths helps locate the action. If one part of the spectrum pulses and another stays steady, the system is telling us that not all regions are participating in the same way. This is similar to listening to a house at night and realizing that only one small machine is cycling on and off, while the rest of the house remains still. The X-ray telescope hears the machine. The optical telescope sees the house. The ultraviolet telescope may notice warmth from a nearby room. Together, the instruments build a more complete picture. No single measurement gives everything. The beauty is in the combination. The detectors themselves are not like ordinary camera sensors in a phone. X-ray photons are difficult to focus because they tend to pass through or be absorbed by mirrors if they hit head-on. X-ray telescopes use grazing incidence mirrors, where the photons skim the mirror surfaces at shallow angles, a bit like a stone skipping across water. This allows the X-rays to be guided toward detectors. It is a clever solution to a difficult problem. If visible light telescopes are like buckets catching rain, X-ray telescopes are more like carefully angled channels persuading very energetic raindrops to go where they are needed. After the photons are detected, the work becomes a mixture of engineering, statistics, and physical interpretation. The raw data must be processed. Instrument effects must be understood. The source must be separated from background. Light curves must be extracted in different energy bands. Spectra must be fitted with models. The models are then compared with physical scenarios: a hot thermal component, an expanding cloud, a changing disk, an absorbing wind, or a region heated by disk impact. The final result may look like a smooth plot in a paper, but beneath that plot is a great deal of careful labour. There is something reassuring about this. The universe can be violent, but our way of studying it is methodical. Near the black hole, gas may be heated to extreme temperatures. A companion may be plunging through a disk. Space-time may be warping the orbit. But on Earth, the response is patient measurement. Scientists count photons, estimate uncertainties, test models, and revise explanations when new data require it. The black hole may behave dramatically. The analysis does not have to. For a QPE, one of the most important observational questions is whether the flare has the same spectrum every time. If each eruption looks similar in energy distribution, that suggests a repeated physical process under comparable conditions. If the spectrum changes from flare to flare, the disk or emitting region may be evolving. If later eruptions become cooler or fainter, the gas supply may be declining, or the geometry may be shifting. If the eruptions disappear and then return, the system may have moved through a temporary change. These details can help distinguish between disk instability and companion interaction models. The shape of the light curve also matters. A fast rise and slow decay can suggest different physics from a slow rise and fast drop. A symmetric flare may point to one kind of heating and cooling. A flare with a shoulder, plateau, or double peak may imply more than one emitting region or more than one interaction. If a source alternates between strong and weak flares, that may hint at 2 disk crossings per orbit, with one crossing producing a brighter response than the other. A black hole's heartbeat is not just a beat, it has a waveform. Astronomers can also split the X-ray data into energy bands. They might compare softer X-rays with slightly harder X-rays during the same eruption. If the hard band rises first, or the soft band lags behind, that timing difference can reveal how heat moves through the emitting gas or how radiation is processed. These delays may be small, but they can be meaningful. In high-energy astronomy, even seconds can matter, because the emitting regions are compact and the physics is fast. A time lag is like an echo inside the system, showing that one part responds after another. Of course, QPEs are faint and distant, so the data are not always generous. Photons may be few, background may be significant, observations may be short. This makes every well-observed eruption valuable. A bright QPE with multiple bursts in one long observation can teach more than a faint source caught only once. That is why discoveries often trigger follow-up campaigns. Once a source is known to erupt, astronomers try to catch future events with different telescopes. They want better timing, better spectra, and a longer baseline. A hidden pulse becomes a target. There is also a sense of anticipation in scheduling these observations. If the recurrence time is roughly known, scientists can try to predict when the next flare may occur. But because QPEs are quasi-periodic, the prediction comes with uncertainty. The telescope may begin watching before the expected eruption and continue afterward. If the flare arrives, the observation succeeds. If it does not, that is also information. Perhaps the timing shifted. Perhaps the source entered a low state. Perhaps the model needs revision. In science, even a missed alarm can tell you something about the clock. This is where the phrase heartbeat becomes useful again. A doctor does not learn only from a perfectly regular heartbeat. Irregularity matters. Strength matters. Rhythm matters. A skipped beat can be important. A changing pulse can reveal changing conditions. QPEs are not biological, of course, and we should not stretch the comparison too far, but the logic is similar. X-ray telescopes do not merely detect that the central engine exists. They monitor how it varies. They turn time into diagnosis. When we say X-ray telescopes hear the black hole's heartbeat, we are really saying that they let us study the region close to the black hole through variability. The inner accretion disk is too small and too distant to image directly in these systems. The companion, if present, is invisible. The event horizon is dark. But the changing X-ray light carries information from the system's edge. Each photon left the source after being produced by hot matter outside the horizon. Each photon survived the journey across space. Each photon reached a detector that recorded its time and energy. Add them together, and the invisible becomes a pulse. That pulse is not sound. It is not a message. It is not the black hole trying to communicate. It is matter obeying physics in a place where the rules are extreme. But because the signal repeats, because it changes, because it has timing and shape, we can read it. A quiet galaxy becomes active in X-rays. A hidden disk becomes measurable. A possible companion leaves marks without being seen. The telescope listens in the only way it can, by counting light. There is a calm wonder in that. Somewhere near a supermassive black hole, a flare rises and fades. The galaxy itself may look still. No human eye sees the flash. No sound crosses space. Yet an instrument in orbit registers the arriving photons one after another, and a pattern begins to form. The heartbeat is reconstructed later, on screens and in graphs, by people who may be sitting in offices, control rooms, or quiet kitchens with cups of tea cooling beside them. The event is enormous, the evidence is precise, the connection between them is a curve. As more X-ray telescopes observe these sources, the heartbeat will become clearer. Future instruments with larger collecting areas, better timing, and improved spectral resolution may catch fainter eruptions and reveal details current telescopes can only hint at. They may find more QPEs in galaxies that once seemed quiet. They may show whether different sources belong to the same family or to several related families. They may trace how one QPE changes from year to year, perhaps following the fading of a disk, the shrinking of an orbit, or the gradual disappearance of the conditions that made the eruptions possible. Once the pulse has been measured, once the X-ray telescopes have counted the photons and drawn the rising and falling curve, the mystery begins to widen again. The flare is no longer just a strange brightening from a quiet, galactic centre. It becomes a tool. It becomes a way to study a place we cannot photograph in detail, cannot visit and cannot recreate in any laboratory on Earth. A quasi-periodic eruption may be a flash of hot gas, but hidden inside its timing are clues about gravity, orbits, and the fate of stars that wander too close to the dark centre of a galaxy. That is what makes QPEs so valuable. They are not only interesting because they repeat, they are interesting because their repetition happens in a region where gravity is strong, matter is hot, and motion is fast. Every interval between eruptions, every change in brightness, every shift in timing, every rise and fall in X-rays is a small report from the edge of an extreme environment. The report is incomplete, certainly. It is written in high-energy light and translated through instruments, mathematics, and models. But it is still a report, and for astronomers, that is enough to begin asking questions that reach far beyond the flare itself. The first thing QPEs may reveal is the shape of gravity close to a supermassive black hole. Far from a black hole, gravity behaves in a way that feels familiar. Planets orbit stars, moons orbit planets, satellites circle Earth. The paths can often be described with the older, simpler tools of Newton's gravity, at least to a very good approximation. But close to a black hole, especially close enough for gas to move quickly and shine in X-rays, Einstein's general relativity becomes essential. Space and time are not just a stage on which objects move, they are part of the structure that guides the motion. If a companion object is orbiting near the black hole and crossing an accretion disk, its path is not a simple closed ellipse. The orbit can precess, meaning it slowly turns over time. The closest approach shifts. The place where it crosses the disk may drift. The timing of eruptions may change, not because the system is careless, but because curved spacetime changes the geometry of the orbit. In that sense, a QPE can become a kind of marker placed on an invisible path. Each flare says, the companion was here, or something in the disk reached this state, at this time. Watch enough flares, and the path begins to show itself. This is a remarkable idea. We cannot see the orbit directly, but the orbit may write itself into the light curve. If the flare arrives a little early, if the next arrives late, if the intervals drift in a consistent way, astronomers can compare that behaviour with models of motion near a black hole. They can ask whether the timing is consistent with precession, with an orbit slowly shrinking, with a disk that is tilted, with a black hole that is spinning, or with gas dynamics changing after each impact. QPEs may therefore let us test how matter moves in the strong gravity region, not by watching a little dot go around the black hole, but by watching the disk flare whenever the hidden motion disturbs it. The spin of the black hole may also matter. A spinning black hole does not merely sit in space. According to general relativity, it drags nearby space-time around with it. This effect is called frame dragging, and it can influence tilted disks and close orbits. If an accretion disk is not aligned with the black hole's spin, or if a companion object orbits at an angle to the disk, the whole arrangement can twist and precess. that twisting may show up as changes in QPE timing or flare strength. One eruption might happen when the companion crosses a dense part of the disk. Another might happen when the crossing point has shifted. In a simple picture, the companion is stirring the same fire each time. In a relativistic picture, the fire, the spoon, and the table may all be slowly changing orientation. This sounds complicated because it is, but the complexity is precisely why the signals are useful. A perfect clock would tell us only one number. A slightly imperfect clock can tell us about the forces disturbing it. A QPE that repeats with small changes may reveal more than a perfectly regular signal would. The deviations may contain the fingerprints of strong gravity. They may show how an orbit evolves near a supermassive black hole. They may reveal whether the black hole is spinning rapidly or slowly, whether the disk is warped, or whether gas drag is changing the companion's path. The irregularities are not merely obstacles, they are part of the message. The second thing QPS may reveal is the existence of hidden companions near galactic centers. A stellar mass object orbiting a supermassive black hole is extremely hard to detect directly. If it is a normal star, its light may be lost in the larger glow of the galaxy. If it is a white dwarf, neutron star, or small black hole, it may be almost invisible. Yet if that object repeatedly interacts with a disk, it can announce itself through X-ray flares. The companion becomes visible by consequence rather than by appearance. We do not see the object, we see what it does. That matters because galactic centers are expected to contain many stellar remnants. Massive stars live and die, leaving behind white dwarfs, neutron stars, and stellar mass black holes. Over long times, gravitational interactions can move some of these remnants inward. Some may end up on tight or eccentric orbits around the central supermassive black hole. These are difficult systems to find because the smaller object is faint or dark, and the central region is crowded. QPEs may act like little signs pointing toward them. Every eruption may say something small and dense may be moving here, close to the black hole, disturbing gas as it goes. If that is true, QPS could help astronomers study a population of objects that is otherwise mostly hidden. How common are compact companions near supermassive black holes? How often do they interact with disks? How long can such systems survive before the companion spirals inward? What kinds of objects are most likely to produce observable eruptions? A normal star, a white dwarf, a neutron star, or a small black hole may each leave a different timing pattern and flare shape. The light curve becomes not only a record of eruptions, but a possible census tool for unseen bodies in galactic nuclei. There is also a connection to gravitational waves. When a small compact object orbits a supermassive black hole, it can gradually lose energy through ripples in space-time. These systems are sometimes called extreme mass ratio in spirals because one object is enormously more massive than the other, and the smaller one slowly spirals inward. Future gravitational wave observatories in space may be able to detect such systems. QPEs may show us some of them through light before we can detect them through gravitational waves, or perhaps alongside them one day. That would be a powerful combination. X-rays could reveal how the object interacts with gas, while gravitational waves could reveal the motion of the masses themselves. For now, that possibility remains ahead of us, but it gives QPEs a special place. They may be electromagnetic signposts of close-orbiting bodies in environments that future gravitational wave astronomy will explore more directly. The phrase sounds technical, but the idea is simple enough. A hidden object circles a giant black hole. Its motion may ripple space-time. Its passage through gas may flash in X-rays. Two different messengers, light and gravity, could one day describe the same hidden dance. The third thing QPEs may reveal is how stars fall apart. This is where tidal disruption events return to the story. A star can orbit safely around a black hole if it remains far enough away. But if its path carries it too close, the black hole's gravity pulls harder on the near side of the star than on the far side. The difference stretches the star. If the tidal force exceeds the star's own gravity, the star is torn apart. Some of the gas escapes, some remains bound. Streams of stellar material curve around the black hole, collide, heat, and may form an accretion disk. This process is violent, but it is also informative. A torn star provides fresh gas to a black hole that may have been quiet before. The resulting disk may shine in optical, ultraviolet, and X-ray light. If QPEs appear years after such an event, as has been seen in at least one well-studied case, they may reveal how the debris disk evolves after the initial destruction. That is important because tidal disruption events are not instantaneous from the black hole's point of view. The star is torn in a moment, but the aftermath can last for years. Gas continues to fall back, the disk changes, the black hole's feeding rate declines, the geometry may settle or warp. QPEs can give us repeated snapshots of this aftermath. A QPE after a tidal disruption event may also suggest that a second object is involved. Imagine a star is torn apart, leaving behind a disk of debris around the supermassive black hole. Another star or compact object already orbiting there then passes through the new disk. Before the disruption, there may have been no dense disk to hit, so no visible eruptions. After the disruption, the disk exists, and the companions' crossings become bright. In this picture, one falling star supplies the glowing material, while another object stirs it. The result is a repeated X-ray signal years after the original stellar destruction. That idea is dramatic, but it also gives scientists a practical framework. If QPS are linked to tidal disruption debris, then the long-term fading of the disk should affect the eruptions. As the debris supply declines, the flares may grow weaker, cooler, shorter, or less frequent. The timing may shift as the disk changes thickness or density. The companion may lose energy through repeated impacts. The system may eventually stop producing QPEs as the disk becomes too faint or too thin. Observing the evolution can tell us how torn star debris behaves after the first bright flare has faded. This is useful because accretion disks formed from tidal disruption events are hard to understand. The debris begins in long, narrow streams, not in a neat circular disk. Those streams must collide, lose energy, and settle. The disk may be tilted, it may be eccentric, it may be thick, it may launch winds, it may feed the black hole inefficiently at first and more efficiently later. QPEs, if they arise from interactions within such a disk, can become probes of the disk's structure. Each eruption may test the density and temperature of the material at the crossing point. Each flare may reveal how the disk changes with time. The phrase "falling stars" should be treated carefully. The stars are not falling in the simple sense of dropping straight downward. They are orbiting through curved space, sometimes on long stretched paths that bring them close to the central black hole only briefly. A tidal disruption happens when the close approach is too close. Some of the star's material then falls inward, but even that material usually spirals, streams, collides, and circles before reaching the black hole. Near a supermassive black hole, falling is rarely a straight line. It is more like being pulled into a dance you cannot leave. QPS may reveal which kinds of stars are involved. A large puffy star may be stripped differently from a compact white dwarf. A star that only partially loses material may survive repeated close approaches, shedding gas each time. A completely disrupted star leaves a debris field but no intact star. The timing and energetics of QPEs may help distinguish these possibilities. If the flares require a companion that survives many passages, the companion must be strong enough or far enough from the tidal boundary to last. If the disk comes from a destroyed star, its mass and angular momentum place constraints on how large and dense the disk can be. These details may sound small, but they determine whether a model is physically plausible. This is where QPEs become a meeting point for several branches of astrophysics. There is strong gravity because the motion happens near a black hole. There is accretion physics because gas forms a disk and radiates. There is stellar dynamics because stars and remnants move through crowded galactic centres. There is tidal disruption, because stars can be torn apart and turned into debris. There is high-energy radiation, because the signal appears in X-rays. A single repeated flare touches all of these subjects. It is a small doorway into a large room. For the listener, it may help to keep the image grounded. A quiet galaxy holds a central black hole. Around that black hole, a disk of gas glows. Somewhere near the disk, a smaller body may orbit. The disk may be made from the remains of a star that came too close. Each time the smaller body crosses the disk, or each time the disk reaches an unstable state, hot gas brightens in X-rays. The burst travels outward through space. Telescopes catch it. Scientists measure the timing and energy. From those measurements, they infer gravity, motion, and the history of falling matter. There is no need to imagine all of this as a perfectly known machine. It is still a young field. QPEs were recognized only recently, and the number of known sources remains small. Different systems may have different origins. Some may be driven mainly by disk instabilities. Some may involve companions crossing disks. Some may occur after tidal disruption events. Some may arise in newly awakened galactic nuclei, where gas begins feeding a black hole after a long quiet phase. The category may contain several related mechanisms rather than one universal answer. That is not unusual in astronomy. Many labels begin broad and become more detailed as more examples are found. What matters is that QPEs give scientists repeated opportunities to test ideas. A one-time flare can be interpreted in many ways. A repeating flare puts models under pressure. The model must explain not only the brightness, but the recurrence. Not only the recurrence, but the changes in recurrence. Not only the flare, but the quiet state between flares. Not only the X-rays, but any optical or ultraviolet history. Each new observation narrows the possibilities. The repetition is not just beautiful, it is demanding. A model involving a companion must explain how the companion survives, how it got onto its orbit, how it interacts with the disk, and why the flare has the observed duration and energy. A disk instability model must explain why the disk cycles on the observed timescale, and why the bursts are so strong. A tidal disruption model must explain the delay between the original event and the QPRs, the structure of the debris disk, and the long-term evolution of the source. These are hard tests, which is exactly why the field is interesting. Easy mysteries are pleasant. Hard mysteries teach more. Gravity is the quiet ruler underneath all of it. It sets the orbital speeds. It shapes the disk. It determines where a star is torn apart. It bends the path of light. It allows a black hole to hide behind an event horizon, while the gas outside reveals its presence. In QPEs, gravity is not just an invisible pull, it is the architect of the timing. The return of the flare may be a return along an orbit. The drift in timing may be relativistic precession. The energy of the X-rays may come from gas losing gravitational energy. The destruction of a star may happen because gravity varies too strongly across the star's body. Every part of the signal points back to gravity doing work in a place where its effects are extreme. Orbits are the visible handwriting of that gravity, even when the orbiting body is unseen. A planet's orbit tells us the mass of a star. A star's orbit around the Milky Way's centre tells us the mass of our own central black hole. A QPE's recurrence may tell us about an orbit too close and too small to image. That is a beautiful continuity. Across astronomy, we often learn about hidden mass by watching motion. QPEs may extend that tradition into the hot compact region, where motion also lights up gas. Falling stars add the history. They tell us where the gas may have come from. A black hole cannot produce an accretion disk from nothing. Matter must be supplied. In a quiet galaxy, the sudden appearance of disk-like activity may be linked to a star that strayed too close. That star's remains can feed the black hole, form the disk, and create the conditions for repeated eruptions. The QPE is then not just a present signal, but an echo of a past encounter. It is the aftermath of one orbit gone wrong, shaped by another orbit still continuing. This layered story is what gives QPEs their richness. The flare we see today may depend on a star disrupted years earlier, a companion captured long before that, a black hole formed over cosmic history, and a galaxy whose central regions slowly arranged the ingredients. The X-ray burst lasts an hour or a day, but its causes may have been prepared over millions of years. Astronomy often works like that. A brief event reveals a long history. As we keep following the pulse, QPEs may become laboratories for questions that are usually hard to approach. How do accretion disks form after a tidal disruption? How do compact objects move through gas near a black hole? How does relativistic precession affect observable timing? How often do stars survive repeated close passages? How does a quiet black hole wake up? How does matter behave just outside the event horizon, where it is still visible but already deep inside the black hole's grip? These questions do not all have settled answers yet, and that is part of the point. QPEs are not a finished explanation. They are a new kind of evidence. They give astronomers something repeatable to watch, in a place where repetition is rare and precious. Each eruption is a small marker. Each marker helps trace the hidden structure around the black hole, and as the markers accumulate, gravity, orbits, and falling stars begin to appear not as separate topics, but as parts of the same system. So the next time we picture one of these black hole pulses, we can see more than a flare. We can see a disk made from captured gas, perhaps from a shredded star. We can see a companion moving through a dangerous orbit. We can see strong gravity bending that orbit and changing the timing. We can see X-rays rising when hot matter responds. We can see the telescope catching the signal from far away. The eruption is brief, but the information it carries is wide. The pulse is still there in the dark, not always bright, not always easy to catch, and not always behaving in the way our simplest explanations would prefer. That is part of what makes quasi-periodic eruptions so compelling. They are not a solved machine with a label on every part. They are a repeated signal from a place where ordinary intuition does not travel well. A black hole sits at the center of a galaxy. Hot gas moves around it. Something changes. X-rays rise. The flare fades. Then, after a pause that is regular enough to be meaningful and irregular enough to be interesting, the signal returns. By now, we have followed that signal from the outside inward. We began with a quiet galaxy that did not necessarily look like it was hiding one of the strangest clocks in astronomy. We moved toward its center, where the supermassive black hole waits unseen. We looked at the accretion disk, that hot, rotating flow of matter that can shine even though the black hole itself remains dark. We considered the possibility of a smaller companion, perhaps a star, a white dwarf, a neutron star, or a small black hole, moving through the disk and disturbing it again and again. We watched the timing become almost regular but not perfect. We let X-ray telescopes turn invisible high-energy light into curves, intervals, and spectra, and we saw how those curves might reveal gravity, hidden orbits, and stars falling too close to the central dark. Still, the full answer has not settled. That is not a disappointment. It is a sign that the subject is alive. In science, some mysteries are vague because we know too little to ask good questions. QPEs are different. They are mysterious because the observations are specific enough to test serious ideas, and the ideas are close enough to compete. That is a better kind of mystery. It has shape. It has evidence. It has names, measurements, source catalogues, telescope time, and astronomers arguing politely through journal papers, which is one of the universe's less noisy but very productive habits. One possible answer is that the disk itself is responsible. In this view, the accretion disk near the black hole may go through a repeated cycle. Gas builds up, heats, changes state, and releases energy in a burst of X-rays. Then the system cools or drains and begins again. That model has a certain appeal because accretion disks are already known to be unstable in many astrophysical settings. They are not calm rings of material. They are hot, turbulent flows where pressure, radiation, magnetic fields and gravity are constantly negotiating. It would not be shocking if a disk near a black hole sometimes produced repeating outbursts. But disk-only explanations have challenges. The eruptions can be sharp, their amplitudes can be large. Their recurrence can be regular enough to suggest a driver more stable than local turbulence. Some sources appear in galaxies that were not long-known active nuclei, which raises questions about how the disk formed and why it began cycling when it did. A disk instability may still be part of the answer, but for some systems, it may not feel like the whole answer. It is a strong suspect, but not the only one in the room. Another possible answer is the companion model. A smaller object orbits the supermassive black hole and repeatedly interacts with the disk. Each time it crosses or disturbs the gas, the disk responds with an X-ray flare. This idea naturally explains the recurrence. Orbits are clocks. Even when the clocks are messy, a companion can return again and again to a similar position, giving the system a repeated trigger. The disk then decides how bright, long and hot each eruption becomes. This model can also connect QPEs to hidden compact objects near galactic centers and perhaps to future gravitational wave sources. Yet this model has its own questions. What is the companion? How did it get onto such an orbit? How does it survive repeated passages? How does the disk respond physically each time? Why do some sources show one kind of timing and others behave differently? If the companion is a normal star, tidal forces and disk crossings may damage it. If it is a compact object, it may survive more easily. But then its formation and capture history must be explained. If it is a small black hole, the object may be nearly invisible except through the flares it causes. The model is promising, but it requires a precise arrangement of gas, orbit, and central mass. A third possibility ties QPEs to the aftermath of tidal disruption events. A star comes too close to a supermassive black hole and is torn apart. Its debris forms a temporary disk. Later, that disk produces repeated eruptions, perhaps because of a companion crossing through it, perhaps because the disk itself becomes unstable, or perhaps because the surviving core of the star continues to lose material. This explanation has an appealing sequence. First, the star supplies the gas. Then the gas becomes a disk. Then the disk begins to pulse. In some observed systems, this connection between a past stellar disruption and later QPE-like behavior has become especially important. But even here, questions remain. Why do some tidal disruption events produce QPEs while many do not? How long after the star is disrupted should the eruptions begin? How does the debris settle into a disk capable of producing repeated X-rays? Does a companion have to be present, or can the debris itself create the cycle? Does the QPE fade as the stellar material thins out? If it does fade, can we predict when it will stop? A torn star may provide the fuel, but the exact engine still needs to be understood. So the mystery keeps ticking because every explanation solves one part and opens another. Disk instabilities explain cycles, but must account for the sharp repeated flare structure. Companions explain recurrence, but must survive and interact in the right way. Tidal disruption debris explains fresh fuel around a quiet black hole, but must explain why the pulse begins, changes, and sometimes vanishes. The real answer may combine these pieces. A star may be torn apart, forming a disk. A compact object may already be orbiting there. Its disk crossings may trigger flares. The disk's changing density may make the timing imperfect. Relativistic precession may shift the crossing points. Over time, the gas supply may fade and the eruptions may change or stop. The clock may be built from several moving parts, none of them simple. That is often how nature works. The first discovery gives us a clean question. Later observations reveal that the clean question lives inside a complicated system. The universe is generous with patterns, but it rarely makes them simple just to be kind. A QPE looks, at first, like a black hole ringing every few hours or days. Then we learn that the ring may come from hot disk gas, shaped by an unseen orbit, fed by a torn star, altered by relativity, and measured through sparse X-ray photons collected by spacecraft. The simple pulse remains, but behind it is a system with depth. This is why future observations matter so much. Every newly discovered QPE adds another example to compare. If many QPEs are found in galaxies with similar black hole masses, that will tell us something. If they often appear after tidal disruption events, that will tell us something else. If some show alternating strong and weak flares, that may support disk crossing models with 2 crossings per orbit. If recurrence times drift in a way consistent with relativistic precession or orbital decay, that would sharpen the companion picture. If some sources behave more like disk cycles without clear orbital signatures, then QPEs may be a broader family of related phenomena. Long-term monitoring will be especially powerful. A QPE caught once is fascinating. A QPE watched over years becomes a story. Does the source fade? Do the eruptions grow cooler? Does the time between them change? Do they disappear and then return? Does the galaxy's optical or ultraviolet light change before, during or after the X-ray phase? These changes can reveal whether the disk is running out of material, whether a companion is spiraling inward, or whether the system is passing through a temporary stage after a larger event. In astronomy, patience is not just a virtue. It is an instrument. Better X-ray telescopes will help too. More collecting area means more photons, and more photons mean clearer light curves and spectra. Better timing means smaller delays and subtler changes can be measured. Better spectral resolution means the temperature, absorption, and possible outflows can be studied in more detail. Future observatories may find fainter QPEs, catch shorter eruptions, or reveal that some sources once thought ordinary are quietly pulsing in the X-ray sky. The class of QPEs may grow from a handful of strange examples into a map of how black holes feed in short, repeated bursts. There may also be a future connection with gravitational wave astronomy. If some QPEs are caused by compact objects orbiting supermassive black holes, then those same systems may emit gravitational waves. Future space-based detectors could, in principle, sense the slow-in spiral of a compact object around a massive black hole. If that happens alongside X-ray eruptions, we would have 2 different ways to study the system. Light would tell us about the hot gas. Gravitational waves would tell us about the motion of the masses. It would be like hearing a clock through the wall while also watching its shadow move across the floor. Neither view alone gives everything, but together they could reveal the mechanism with extraordinary detail. For now, the dark still keeps some of its privacy. That is fitting. Black holes are not objects that surrender all their secrets at once. They reveal themselves indirectly. They bend light, they move stars, they heat gas, they disturb disks, they produce jets, flares, winds, and in these rare cases repeated eruptions. The event horizon remains a boundary, but the region outside it is full of evidence. QPS belong to that evidence. They are not coming from inside the black hole, but from matter close enough to feel the black hole's strongest influence while still visible to the universe. There is something important in that distinction. The darkness itself does not speak, but the matter at its edge does. Gas spiraling outside the horizon becomes a messenger. A companion crossing the disk becomes a hidden hand. A torn star becomes fuel. X-ray photons become data, and data becomes understanding. Slowly, carefully, never all at once. The black hole stays black, but its surroundings make a record. If you imagine one of these systems now, perhaps it no longer looks like a simple dark hole in space. It looks like a small central stage inside a vast galaxy. The black hole is in the middle, unseen but dominant. Around it is a disk glowing in high-energy light. Somewhere nearby, perhaps, a smaller object follows a dangerous orbit. The disk is not perfectly smooth. It may be warped, changing, thinning, or freshly made from a destroyed star. At one moment the system is quiet, then gas heats, X-rays rise, the flare reaches a peak, it fades. The telescope records the change, hours or days pass, the hidden process returns. The pulse repeats. That repetition is the reason we can study it at all. A one-time flare would still matter, but a repeated flare gives us more chances. It lets astronomers predict, follow up, compare and refine. It lets models face multiple tests instead of one. It turns a distant event into an ongoing conversation with evidence. The universe says something once, and we wonder. It says it again, and we start measuring the interval. Still, even repetition does not make the subject easy. QPEs sit at the meeting point of several difficult areas: black hole accretion, stellar dynamics, tidal disruption, strong gravity, X-ray radiation, and time-domain astronomy. Each field has its own uncertainties. Put them together, and the result is rich but demanding. That is why the answer is not likely to be a single sentence. It may be a set of conditions. A QPE may require the right black hole mass, the right gas supply, the right disk structure, and perhaps the right companion orbit. If one ingredient is missing, the pulse may not appear. If the ingredient changes, the pulse may alter or stop. This may explain why QPEs appear rare. They may require a special alignment of circumstances. A quiet galaxy needs a black hole, with enough gas nearby to shine in X-rays. The disk must be compact and hot. A companion, if involved, must cross it in the right way. The system must be observed at the right time with the right instrument, for long enough to catch multiple eruptions. Even if QPEs are more common than we currently know, they are not easy to find. They are small, temporary rhythms hidden inside distant galactic centres. That hiddenness gives them a certain quiet beauty. Not beauty in the decorative sense, and not in a way that softens the violence of the physics. It is more practical than that. The beauty lies in the fact that something so far away, so compact, and so extreme can still leave a measurable pattern. A few photons arriving in a detector can reveal a process near a black hole. A changing graph can point to a hidden orbit. A repeated flare can suggest a star's remains, a disk's instability, or a companion moving through curved space-time. The universe can be obscure, but it is not silent. As the mystery remains open, it also remains useful. QPEs may become one of the ways we learn how black holes wake up after quiet periods. They may show how disks form from torn stars. They may reveal compact objects in galactic centres. They may test predictions about relativistic orbits. They may help prepare for future gravitational wave discoveries. Even if the class turns out to contain more than one mechanism, that will still teach us something important. Nature often uses similar signals to reveal different machines, and sorting them out is part of the work. For a science for sleep journey, there is a gentle lesson in that unfinished state. Not every mystery has to close before we can rest beside it. Some questions are steady enough to hold without needing immediate answers. QPEs are like that. The pulse repeats, the models improve, the telescopes watch. The dark remains dark at the centre, but the light around it gives us enough to keep learning. So if you're listening now with your own room quieting around you, you might picture that distant galaxy one last time. It looks calm from far away, just one small glow among many. Deep in its centre, a black hole waits. Around it, gas circles and heats. Somewhere in that hot flow, a process repeats. Perhaps a companion crosses the disk. Perhaps the disk itself cycles. Perhaps the remains of a fallen star are still settling into the black hole's grip. Then the X-rays rise again, a brief brightening near the edge of darkness, invisible to our eyes but clear to the instruments watching above Earth. The flare fades, and for a while, the galaxy returns to quiet. But the quiet is not empty. It is the pause between signals. It is the waiting part of the rhythm. Astronomers will keep watching, because the next flare may arrive with one more clue. It may come a little early. It may come late. It may burn brighter than before, or softer, or not at all. Any of those outcomes matters. Each one changes the shape of the question, and perhaps that is the right place to leave the black hole for now. Not solved, not silent, and not fully hidden. It is still there in the dark, surrounded by hot matter, curved space, and patient uncertainty. Somewhere far away, the almost clock keeps its strange time. A galaxy that once looked quiet carries a pulse at its centre. A black hole that cannot shine still teaches through the fire around it. And in the soft work of counting X-rays, comparing intervals, and waiting for the next rise in the curve, the mystery continues, still ticking gently in the dark.